Welcome everyone to EBAA Conference 2024. And thank you, Lynn and team, for a very delicious start to the conference. I think they My name is Susan George. I'll be doing the introductions for the sessions. We'll start by acknowledging the Buru-Barangal people of the Darug Nation on whose unceded lands we meet today. We acknowledge their frontier wars, their fallen warriors, and their elders, past, present, and emerging. Now, I'll go on to some housekeeping items. We've got a refreshment area at the back, so feel free to help yourself to coffee and tea. We've got bathrooms, so we've got one at the end of the corridor at the back, and then we've got a block of toilets on the opposite side of the road. So it's the red brick building C27. So if this one's occupied, you know where to go. In case of an emergency and we need to evacuate the building, the assembly area is out there on the grassed area. The sessions will be recorded, so the talks and the Q&A. We request that that you keep your mobile phones on silent during the sessions. We've got a conference booklet at the back of the room, so that's got your program. It's also got a map, so that's really useful. So if you want to grab one of these on your way out. I'll now invite Peter to deliver the President's welcome. He doesn't really need an introduction, but I'll do it anyway. Peter is a founding member of EBAA and has served on the committee since 2000, and he's been the EBAA president for about 10 years now. He's a professional builder and has been actively engaging with earth buildings for close to 42 years in design, construction, education, research, advocacy, leadership, and community development. Peter, along with Stephen Dobson, have been actively engaging with NatHERS to incorporate low-density earth material values in the NatHERS assessment for thermal comfort. And we're really excited to hear more about this development in Peter's talk today and tomorrow. So, up to you, Peter.
We've got Dr Jim Carfrae over in UK who follow me. So he's standing by. I'm going to have to read some of this. I apologise for that. And I'm using a whole heap of acronyms. And I know they suck the oxygen out of the room, but there's just acronyms every CSIRO, NatHERS, EBAA. EBAA is a friendly one, but there's lots of them. So apologies for that. So this conference is themed Optimising Earth Wall Materials to achieve NatHERS 7-star compliance. So there's a long history to this, and I'll try and keep it short, but good luck with that, but I'll try. So in early 2019, after perhaps 16 years of sound argument and submissions to CSIRO and NatHERS, they finally agreed with EBAA's request to look at developing an alternative pathway for naturally ventilated, naturally conditioned buildings. That's a huge achievement for EBAA. There's lots of architects have been calling for it for a very long time. So EBAA has championed the introduction of a more appropriate pathway for assessing all passive low energy buildings, so tropo buildings, lightweight buildings in the tropics, all those sorts of buildings, not just those built of earth. So we're hoping that a pathway that's more fair to us will unblock the potential for architects and designers to use passive low energy buildings again, and that the results that will come from the different way of assessing it will better inform legislators and regulators. And we need to be judged by the same tools, though with a more appropriate metric like safety, health, adaptive comfort achieved, rather than how much energy is required to achieve comfort with an air conditioner. So that's the problem. So there needs to be respect for buildings that maximise natural gains from external conditions. So it's what you can pick up from the cool of the night and the heat of the day, and store in the building and use it later. So that's the thermal mass, the fabric energy storage is the driver of natural conditioning, being able to condition the air that comes through the building. So it's a return to the first principles of energy management and efficiency, negating or minimising energy demand, and especially peak load demand through passive low energy architecture that's designed appropriate for climate. So I'll just... So this approach is akin to designing passive low energy buildings to operate effectively like sailing boats, not like motorboats. Buildings that rely on air conditioning are like motorboats. So CSIRO and NatHERS at the present time setting up working group and commenced the process of establishing an alternative pathway. All I can confirm is that they've got a work program. It's still on the work program, but it's well behind schedule, and we haven't given up on it, and we won't give up on it. So that's what I mean. That's the difference between the two. Is they're both boats. They can go places on water, but ours is using the equivalent of the natural conditions like the wind to get somewhere, whereas the other one you judge it on how much diesel it's using per nautical mile. So following on from the success in 2019, I'm also pleased to announce for the first time publicly that in late 23, after a lot of to and fro, EBAA, NatHERS, CSIRO, EBAA, NatHERS, EBAA, COB-BOJ, EBAA, CSIRO, NatHERS, and it went on quite a bit between all of us, then eventually 3 new materials were added to the NatHERS library. Our request was only possible being supported by a report from the Environmental Building Research Group at the University of Plymouth in the UK, and Jim was part of that. So until then, only earth materials in the NatHERS library were, the only ones there were rammed earth and pressed earth blocks at about 2,100 kilograms per cubic metre and mud brick at 1,750 kilograms per cubic metre. Therefore, until then, only rammed earth and mud brick could be modelled for energy efficiency in NatHERS. So the 3 newer low density materials added represent earth building techniques that have become more popular in recent years, and they also represent what can be easily achieved to lower the density of existing earth building techniques like mud brick and rammed earth, for example. So COB is one of those. COB was actually one of the earliest techniques used in New South Wales colonies, and there's been a COB revival in recent years. The same subsoil material used to make mud bricks and COB, both the same, though fibre is usually added in the form of straw to control shrinkage in COB, so that makes it lighter. So it's about 175 kilograms per cubic metre lighter, so it's usually about 1,600 kilograms per cubic metre. So that's what we've asked for, the values for that in the library. Mud brick can be produced with a COB mixture containing fibre to achieve that value as well. So you can make mud bricks the same as COB bricks, but they're just COB bricks, I guess, yeah. Okay, so rammed earth and pressed earth bricks can be produced down to this density too, through the, instead of fibre in rammed earth, you've got to put in lightweight aggregates. So there's a choice of aggregates, various ones you can use. I've experimented with some of them: pumice, scoria, bottom ash, foam glass, and expanded clay. This product that Ryan's selling is called Clinkax expanded clay. So both mud brick and COB can be further reduced down to about 1,000 kilograms per cubic metre through the inclusion of even more fibre. Could be straw, sawdust, paper pulp, cow manure, hemp hurd, and much less sand and silt than usual. So you're taking out the silt and sand and gravels that are the heavyweight inert materials in the earth building, and you're swapping them out and using clay to stick all the fibre and different fibres together. So you can get down to 1,000. And that's the density of water or hardwood. So mud brick can float, and I'll show you that tomorrow. Hopefully. Yeah, mud brick boats. That's right. So earth walls can be produced down to around 400 to 650 kilograms per cubic metre, which is half the weight of water, using the light earth method. Light earth method is essentially straw material bonded with very little clay, so just a clay slurry. And did you bring the big? Where are the boys? Bring the big cannon or the big tube?
Yeah, it's all set up.
Yeah, good. Okay. So you just pour a little bit of clay slurry in, and it just goes through the straw, and then you tamp that into formwork, temporary formwork. At this sort of density, it's non-load bearing, so you've got studs taking all the loads, and it gets rendered inside and out. But the looks like a bit of a woolly mammoth, doesn't it? But it's just get rendered with earth on the inside and lime render on the outside, I guess, or earth both sides. But it can be used. It could also be used between floor and ceiling joists to reduce sound transmission, provide insulation and little energy storage, and further cut embodied energy. So it can be you can do a fair bit with light earth in buildings. I think it's good in old buildings that you've got stud work there and you want to fill it up, improve the performance of the building. So now earth builders in Australia can produce, and not just produce, but model a very wide range of earth building materials with densities from 650 kilograms per cubic metre, which is around the density of softwood, to more than 3 times that density at 2,100 kilograms per cubic metre, which is about almost the density of concrete. So lightweight softwood right through to concrete, all with earth building. So we've got a huge range of earth materials having very different thermal characteristics to respond appropriately to a huge range of climates that we have in this country. So light earth method has an insulation value similar to hempcrete, and that has been able to comply with thermal assessments in cold climates in relatively thin walls. Earth at 1,000 kilograms per cubic metre, density similar to that of timbercrete, which has also been able to gain approvals in Victoria in cold climates, albeit with a thicker wall. These colder climates where approvals for rammed earth and mud brick were difficult. The beauty of earth walls with 1,000 kilogram density is that it costs very little extra in terms of dollars and embodied energy to build a wall, say 400 thick. So in England, with much colder climates, it was quite common to do 600 thick walls, 2-foot thick walls. Though our climates here are milder compared to those regions of UK and England. Okay, so you can still do cavities in earth walls and fill them with insulation, or insert insulation directly into earth walls and gain compliance, which is what a lot of rammed earth people do. Though this adds to time and costs and creates potential for practical, structural and poorer ecological outcomes. If you're using various foam boards, for example, there are better insulators that you can put in there. Building them into stabilised rammed earth is not a big drama, but trying to get them an insulated cavity in a mud brick wall or a load bearing out in the weather is problematic. So it's still an option, and options are useful. So we're absolutely not suggesting that designers and earth builders simply swap out what they had planned, like rammed earth walls or mud brick walls, for lower density earth options. That's not it. It's not the way to design for climate. It's not what it's about. Some warmer climates, like Sydney and Perth and northwards, and especially inland Australia, actually favour high thermal mass, and modelling should reflect that. I'll have more to say about that tomorrow. What we know is that lower density values will help to achieve compliance, and they will to a lesser extent help us better design for climate until the new assessment pathway is in place. So I think I've got out of whack here with my slides, but there's all the densities there. I'll leave that up, I think. So the unique advantage of Earth is its widespread abundance and availability, its minimal low embodied energy, its low material cost, and ability to produce thick walls cheaply through sourcing all of, or the bulk of, materials on-site or locally, reducing the material cost and the transport costs. Of course, it has other benefits over some other materials, like the ease of use and workability. It's non-caustic, non-toxic, non-allergenic, non-flammable. It's got the best fire resistant levels. It's got the best possible bushfire attack levels. Can achieve flame zone. It doesn't rot. It doesn't provide homes for vermin. It doesn't corrode. So it's got a lot of other potentially advantages over other things. So and it can last as long as required. And it can be easily reused, and it's infinitely recyclable. So it can be the structural load-bearing element, as well as the waterproofing, cladding, lining, permeable membrane, insulation, all in one. So earth material can be used in floors, ceilings, roofs, and furniture. Earth elements can collect, store, and release moisture and thermal energy, thereby balancing both temperature and humidity and controlling condensation. And now it can be configured to respond appropriately to climate by optimising the thermal characteristics through varying the density and or the thickness. So earth material elements are extremely useful in passive low energy architecture. So we can now offer a great range of materials required to optimise design for a huge range of climates found in Australia. So the big push from EBAA for the inclusion of the three newer low density earth materials, and the reason for the theme of this year's conference are that the changes to the National Construction Code 2022 have been brought in the pending implementation of NatHERS 7-star and low efficiency, together with the slow and uncertain progress with NatHERS alternative pathway for passive low energy buildings. And also, though we're able to achieve beyond carbon zero already in terms of full life cycle design, which may be the target for everyone else by 2050, we can also do better in terms of design for climate, and we can also do better in relation to meeting NatHERS compliance in colder climates. So indeed, some pioneers and innovators in Australia, especially those in colder climates, are already doing so. They've been using the light earth method and lower density earth materials to reduce predicted heating loads and thereby comply with NatHERS already. So they should be rewarded and encouraged, along with others with others interested, by being able to model what they have achieved. So whether we like it or not, whether I support NatHERS 7 stars, I don't really. I've got problems with it. It's the reality assessment and the assessment for compliance with energy efficiency in most of Australia is using NatHERS regulation mode for now. So we're stuck with it. So we don't know how the assessment pathway for passive low energy buildings will evolve. We've certainly contributed ideas to how this could work, and Marci's talk may touch on that tomorrow. We anticipate the low energy alternative assessment pathway for passive low energy buildings would run alongside the current NatHERS regulation mode with assessors, which assesses the energy efficiency of buildings that are reliant on air conditioning and seeks to minimise losses. So we're not trying to do that, but we'll probably run alongside that because everyone else will be trying to do that. So passive low energy earth homes are for people to live safe, healthy and comfortable lives in affordably. And considering climate change resilience for the life of the building, the design should take into account lifestyle and climate. I reckon the whole package should be as sustainable as possible, so low embodied energy, the rest of it, and help to reduce greenhouse gas emissions by as much as possible, as quickly as possible, and help the transition to renewable energy as well. So I reckon if we can achieve all of this, no problem, sail on. That's the way, and I think we should be judged on those things. Certainly, the principles of passive low energy are as old as earth building itself, and as old as good vernacular architecture. Socrates wrote about passive design in Greek times. In Roman times, Pliny the Elder wrote about the use of lightweight mud bricks that could float being used in alpine climates near Aragon in the Pyrenees, whereas on the plains below, heavy construction, of stone and normal mud brick was being used. So the peasants knew about this sort of stuff, and someone like Pliny the Elder was cottoned onto it and wrote about it. Okay, so we know we can see how popular rammed earth and mud brick were in hot climates around the world, cob in cooler climates, and wattle and daub in even colder climates like Scotland and Ireland and places. So, and eventually light earth method in cooler climates still, sort of England, Germany, places like that. I've missed a few slides, sorry. So we spent a most pleasant night in a Pisé barn conversion near Lyon in Rhone Alps, near region of France. So you can see the Alps, you can see the snow with a big jump up to it, but it's still a pretty cold place with sub-zero for 12 weeks or something or other. The owner was an architect and he was forced to build airtight insulated boxes for a living due to the regulation. He said that this Pisé home was comfortable all year round. It was kept totally warm by a small Italian wood heater during the long cold winters. It was summer when we stayed there. It doesn't look like summer there in the photo, but it was in the evening. And it was a warm day, and it was one of the nicest nights we had in our time over in Europe. It was very comfortable. So there are very different design solutions used in vernacular designs that evolved across the world and across Australia. Very different designs and material compositions evolved over time. Thank you. Yeah, I've got time coming from the wings there. That was a distraction, sorry, where was I up to? That worked for the occupants in that particular climate in the days before the technological fix for poor design wasn't an option. The wisdom of the age is what we wish to encourage, though we can do better than that. We can improve what we do. So yeah, I began my career in passive solar design. I'll touch on that tomorrow, but later I was asked to go and work in the Philippines and in Central Australia. People said, "Oh, you're going to Central Australia, you better do straw bale, it's so hot out there." It's not the case. It's the wrong approach. You go heavy. I'll talk about that. Went to the Philippines. I thought, oh my God, I must be silly going to the Philippines and doing earth building. But I read a book that was Appropriate Climate Responsive Design Principles, and it worked out well over there. So it did work well in the tropics, but you had to design the building according to climate. So I'll talk about that tomorrow. So I was doing some lightweight stuff. I took bricks to Boomerang Beach in 2006. No one was interested. 1,000 kilos. There's no real interest in it. So I built a cob cottage, 1,600 kilos, and I reduced the back wall to 1,000 for an experiment. Rita's cob cottage in 2019. Now in New South Wales, we haven't been pushed down this path of low density because we've got BASIX, and BASIX is friendly to earth. God love them. and they could understand we were giving value and NatHERS wasn't recognising, so there's a pathway for us there. However, in Victoria, the industry went kaput pretty much when they brought in even 5-star NatHERS. And but there were some members of EBAA, notably Gabby Frutoff and James Henderson and Vasco Dragoski, who started doing light earth method down there. And they were using 650 kilograms, 200 walls, and that couldn't be modelling NatHERS. If anyone can get down to 400, we'll get that in the library. It's not a problem. They've opened the doors for us. They said they'll take lower density. So I think Kenny Lemur is demonstrating light earth method tomorrow morning. So rammed earth and compressed earth blocks can be optimised down to 1600. We talked about that, using the low density aggregates. Ryan will be talking about that tomorrow. Verena Maeder from New Zealand, Solid Earth in New Zealand, will be talking about her experience making low density mud bricks, and they've got cold climates over there and problems with thermal stuff too. So I'm sure Jim will be touching on the Cobb-Bose method, which is there. So it's a 600, almost 600 thick. I think it's a bit thinner than that. Yeah, 556. I looked at the latest figures, and the Cobb part of it is 1430 kilograms, and the outside of the wall inside is 1430, taking the weight of the roof load. Outside is 340 kilograms. They've gone really low there with clay and hemp, I think. And because they're over there, they've got a target of a U value of 0.3, I think, and this one's down to 0.28. So hopefully they're succeeding with that. Okay, so thank you. That's it from me. And so this is sailing here. These guys, high performance sort of stuff. That's what we try and get our sailing up to. Right, yeah, that's it. So Jim and I have a common birth year and an common interest in Cobb, and an interest in possible retirement as well, both of us. Jim and Steve Goodhue and a few others from the Cobb-Bose project, and Steve Dobson and I we've had plenty of fruitful and enjoyable hours on Zoom discussing earth building. Their project aim was to revive Cobb as a sustainable solution to low embodied construction with modern day thermal compliance. So we have our thermal compliance issues here, and we know a bit about margin thermal stuff too. So hopefully the experience was mutually valuable. Certainly was from EBAA's point of view, because we received a test report to gain inclusion for the 3 new materials for free. Cyro is going to cost us $16,500, and they were able to do it for free, which is great. So I hope that they got more out of it than just our Aussie charm and a letter of heartfelt gratitude. So before you answer that question, Jim, I haven't finished. So the Cobb-Bose project is an example of what can be achieved for earth building in just 6 years. In that time, you completed research and development of a new Cobb system, completed the test building, started real and monitoring of it, started real building projects, developed and conducted training manuals, everything, a whole lot. You achieved everything that we've wanted to achieve in Australia for the last 15 to 20 years. You've even had time to win several big sustainability awards, but it does show the value of having an environmental building research group at the university, something we had when Cyro was involved in the experimental building station. And it certainly does show what support from the European Commission, along with a very healthy budget in excess of €4 million, and a great team of assembled team, including members of EBAA's UK equivalent, EBAA, EBAA, I think it might be, can achieve. And I'm just guessing that it's lucky that Brexit wasn't any earlier than it was. Anyway, welcome, Jim, and good morning.
Good morning. I hope you can all hear me. So thank you very much to Peter and to EBAA or EBAA. I'm very honoured to be asked to give this presentation. I think you're taking a certain risk in asking a scientist to give a keynote, because there's going to be lots of graphs and figures and very little light entertainment. I'm Jim Carfrae. I've worked on this COBOGE project at the University of Plymouth for the last 6.5 years, and I'm going to talk about, firstly, I'll just give an outline of our project and what we set out to achieve and what we got, and then I'm going to talk more specifically about the testing that I did on behalf of Peter and Stephen and EBAA on the medium weight cob blocks. So this modest building here is important because this is our prototype building using the COBOGE cob walling system, and it is the first all earth and fibre building in the UK that has achieved building regs without additional insulation in the last 10 years. So it's a very important building from that point of view. It's also an important building for us because it's a living laboratory. Through this building, we're able to record a lot of data. We're taking constant measurements of its performance inside and outside. We've got probes measuring the temperature of the wall at 6 points going through the wall, so we can get complete temperature profiles of how the building works in both in winter and in summer. Going back to where all this started, this is traditional cob as used in the southwest of England. There are different traditions for using cob around the world, but they're all pretty similar. This is a mass wall building system that uses a wet mix. So layers of subsoil mixed with straw are laid upon a plinth. So there'll be some sort of dwarf wall at the bottom of the wall, and it's laid in layers or lifts of about 700 millimeters high. That's high-ish. They can be 500 mil as well. Each layer has to be allowed to dry enough to support the weight of the next layer. So it is a time-consuming, labor-intensive process. And then once the walls have dried enough, the windows and doors can be cut out afterwards. And in terms of design, traditionally, it's always needed, in the Devon vernacular, a good hat and boots bay. So that means it has to be the boots bring it off the ground, and the good hat is an eaves overhang that protects the walls from moisture. But actually, what has proved disastrous for cob building in terms of its longevity is neither the good hat or boots, but it's in fact that people have been re-rendering cob buildings in a cement render, cementatious render, rather than with lime, which stops the vapor permeability of the wall, so moisture builds up in the cob and eventually it collapses. But that's not today's topic. So a couple of examples here of cob in the southwest of England. Very traditional row of cob cottages on the left. This is a village called Start Bay near the coast in England, which has the highest concentration of cob cottages around. And then we have the house called Dingle Dell, built by Kevin McCabe. This was completed, I think it took a long time to build. It was featured on the television program Grand Designs, and I think it was completed within the last 10 years. But the difference with this house is that in order to comply with building regulations and get permission to be built, the whole house had to be encased in 150 millimeters of expanded foam insulation. So although it is a cob house, it is a cob house with extruded foam insulation around it. So not necessarily the best news environmentally. It also renders the wall non-permeable, so they have had some issues with moisture management within the house. I know that now it's working fine, and it's a very spectacular building. So the problem with contemporary cob, in this country, in the UK, is the building regulation. The part of the building regulations, part L1A, the conservation of fuel and power, which deals with the thermal performance of a building, and it has stringent regulations about every part of the building. So there are what they call the limiting fabric parameters for every aspect of the building: the roofs, walls, floors, party walls, swimming pool basins, and so on. But the important thing here is the limiting performance for the wall, and that is 0.3 watts per meter squared Kelvin. That's a U value measurement, which is the inverse of resistance, but is calculated the same way. And that's what we are up against, because in order to achieve this figure, a traditional cob wall would have to be at least 2.1 meters thick. I have to say that since this project started last year, a new version of the building regulations came in, and that figure for the wall has been reduced from 0.3 to 0.26. So like yourselves in Australia, we're up against a constantly changing set of regulations. So we started developing an insulation for cob, or an insulating cob element that we could put on our walls. We didn't want to cover our buildings with 6 inches or 150 millimeters of expanded foam. We wanted to use natural materials. And after testing a variety of fibers, we decided to use hemp shiv, or hemp hurd, as it's known, because that had the best insulating qualities of any of the fibers we tested. And we've made a series of test pieces here that you can see, using different kinds of clay slip and different quantities of hemp hurd. These are then processed to get ready to put in a heat flow meter. There are temperature sensors attached to each face of it, but also the heat flow meter itself has a cold plate and a hot plate, and it measures the conductivity of a material by timing or measuring how much energy is passed from the hot side of the plate to the bottom side. So you can see a sample in the heat flow meter there, and there's a plate pressing down on the top of it, which is at 20 degrees, and then at the plate at the bottom is at 0 degrees, and it's measuring the transfer of heat between the hot side and the cold side. Can get a series of results for our different insulating mixes. We can plot them on a graph, and there are going to be a few of these in this presentation, I'm afraid. And we can compare those insulating mixes with traditional cob. So in this graph, going along the horizontal axis at the bottom, we've got density in kilograms per meter squared. So Peter mentioned you had a middle weight of 1,000 kilograms per meter squared. And then the traditional cob, which is at just below 1,600 here, which has got 2% straw in it. And then there's another sample here with no fiber at all at the top, which came in at just under 1,800 kilos per cubic meter. And then the conductivity figure up the side here, the fibers on their own were achieving conductivities of 0.05. The very lightest insulating mixes we got were 0.1, and most of them were around between 0.15 and 0.2. So as you can see on this graph, they are encouragingly all following the same line. So there's a definite relationship between density and conductivity, and also they're all achieving pretty good results. And so the solution for us in the UK was not a medium density wall. It had to be a composite, because we can therefore optimize each half of the wall to do the job that it's designed for. So one half of it is made of a dense cob mix, around 1,600 kilos per cubic meter. and the other side of the wall is a lightweight mix of clay slip and hemp hurd, which in these cases was around 350 kilos per cubic meter. And these are little test specimens that we started building up to get an idea of how the materials work. We were also then able to calculate the resistance and therefore the U value for our composite wall before we started to build it. We did these sums and we had to talk to building regulations about whether they thought our wall would be compliant before we could build it. And these were the sort of sums we used to demonstrate. So all the elements of a wall are included in the U value calculation. So you've got internal and external surface temperatures. We've got an internal earth plaster. Then we've got the dense cob with 2.5% flax straw. Then a lightweight cob of 50% hemp shiv or hemp hurd. And their densities were 1423 and 340 respectively. And I think, as Peter said, we're a wall that's the basic materials are 600, so we got 300 each of the two different cob mixes, but with the external finishes that can go up to 650 or 660 millimeters thick. And then you add the various resistances together and you get a total resistance figure of 3.78. And then if you take the U value from that, which is the inverse of the resistance, so 1 over 3.78 is 0.26, which achieved our aim of getting a U value that was under the 0.3 of the building regulations at the time. These results are encouraging because even without additional materials, they comply with the regulation. So in other words, the wall is performing without the addition of any extra high embodied energy insulations. And just a reminder of that's the figure from building regulations of 0.3. So what has this got to do with Australia? So I think Peter's alluded to this. We were contacted by Peter Hickson and Stephen Dobson back in 2019. And after many discussions about the state of play, both in the UK and Australia, as regards the different regulations, Peter talked to us about doing a series of tests on medium density blocks in order to see whether they would work for Australian thermal regulations and to see whether we could get some sort of form of measurement that would comply with the NatHERS ratings. Rather than a composite wall, Peter and Stephen were both keen for us to look at a medium density mix because your thermal regulations at that time were not as stringent as they are in the UK. So we're looking at materials with about 1,000 kilograms per cubic meter. Conventional cob has a fiber content of 2.5% or around that figure and a density of around 1,600 kilos, as Peter was saying earlier. So for these tests, 3 cob blocks were prepared with varying quantities of fiber, 8%, 10% and 12%, which gave a densities of between 916 and 1,077 kilograms per cubic meter. So we're looking at different mixes in the same ballpark. And the first thing there is you can see that there is a very clear relationship between the fiber content and the density of the cob mixes. I mean, it's common sense, but here it is displayed on a graph and the figures recorded there. So if the fiber content is 2.5%, gives a density of 1635 in that particular sample, then the 8% was 1,077, 10%, 936, 12%, 916, and the 50% fiber mix, which is the one we were using, which in this particular case has a density of 430, they all fit along a handy graph like that. And throughout this process, you'll see that there are very clear relationships between the fiber content, the density, and therefore the conductivity or resistance of the different materials. This is the heat flow meter that we used, I've spoken about already. It's a fairly simple looking device, the size of a sort of shelf top fridge, but they cost an enormous amount of money. So that's where a chunk of the very generous European funding went. to buy this machine, and it's connected to its own computer with a screen which gives a readout of the process. And all these tests are conducted at 3 different temperature ranges, which I'll talk about shortly. The photograph on the right-hand side shows some other samples we were testing for another university, where they're looking at extruded cob. So these cob samples have been extruded from a machine, and one of them there is hollow, and the next one along, which you can barely see, has got different lightweight mixers inside the extrusion. So we're doing testing for a lot of different people as well as yourselves. And here are the complicated results that come out of the machine. One of the things I was going to allude to here was the different temperature ranges. So in every case, the difference between the hot plate and the cold plate is 20 degrees. But as they go up, it goes from 0 to 20, then from 10 to 30, and then 20 to 40. And in each case, you get a similar thermal conductivity and resistance figure. So it's just the process, and the ISO, the international standard, demands that you do the same test at different temperatures. So these are results from the 8% fiber, the 10% fiber, and the 12% fiber. And I can extrapolate from that a mean of all the conductivity figures, which is shown below. So the conductivity for the 8% fiber was 0.36, for 10% it was 0.32, and for 12% it was 0.31. So those figures don't go in a straight line, as you might imagine, and that's probably due to the natural variance of using natural materials. So here am I, as a sort of scientist, measuring things very precisely. You'll see down to 5 decimal points here, but in fact what we're dealing with is a mixture of mud and straw and small stones, and there is a lot of variance within the samples as well. And again, density and conductivity have a relationship within just these 3 samples. And you can see that the middle sample, the 10%, does not sit in the middle of the other 2 samples, partly again because of the variance of the materials. And then to give those figures further context, we can add them up to all the other measurements we've taken with that machine at the University of Plymouth. The 3 Australian samples there are highlighted in red, and you can see that they sit along a norm, a curve, which relates to all the different figures. So we can have confidence in our measurements. They're not the best, they're not the worst. They sit very close to the mean, and this is part of the evidence that was enabled NatHERS to include them in the library. So that was the thermal conductivity measurements we did for the samples. I'm now going to talk a bit more about the specific heat capacity of materials. This, as Peter alluded again in his introduction, is an essential part of a natural building. And the traditional story with cob in this country, people will tell you over and over again, if they live in a cob house, the house stays cool in summer and warm in winter. So thermal mass is often discussed in the role that these materials used in construction can play on the passive control of internal environments. And the property of a material to provide that thermal mass is called specific heat capacity or volumetric capacity. And importantly, for people like myself, it can be measured. So again, usefully for us, the same machine that measures conductivity can also measure specific heat capacity. So here is the result of the measurements of the specific heat capacity in joules per kilogram per degree Kelvin for the 3 samples. No, sorry, not for those 3 samples. These were 2.5% fiber mixers. These were lightweight mixers, just an example. And again, I'm confusing myself. It's early in the morning here. These are not the lightweight samples. They're the structural mix, the 2.5% fiber with a density of 1635 kilos per cubic meter. And this value is called a CP value, which is also known as specific heat capacity, with an average of 879 joules per kilo per degree Kelvin across the 3 temperatures. Now, the 3 midweight cob samples for Australia were also tested for their specific heat capacity. To give context to those results, we've also added the representative samples of cob with 2.5% fibre and light earth with 50% fibre content. Again, a complicated mess of figures here that can be extrapolated down to a mean specific heat capacity figure for each of those mixes. And you'll see that, again, they fit on a handy graph, except for the 12% fibre mix, which sits outside this specific heat versus density graph. And that may be something to do with the fact that it didn't fit very tidily on the other graphs as well. This is when you come to measure things in science, there are always outliers, and they sometimes tell you more than the ones that fit within the curve every time. But specific heat capacity, you can see here, it varies from 879 to 1053. So it's not a particularly wide range for a very different range of densities. That's because specific heat capacity is a quality of the material itself. It doesn't take into account the density of the material. So you need to turn it from specific heat capacity to volumetric heat capacity, which takes the density into account. So this is a bit like comparing a ton of lead with a ton of feathers. They might both weigh the same, but they occupy a very different amount of space. And therefore, it's the density which gives us the more useful figure. And if we convert those specific heat capacities into volumetric heat capacity, we get a range of figures which represent the different densities more accurately. So the dense cob, the 2.5% fibre cob, has a volumetric heat capacity, which is megajoules per degree Kelvin per cubic meter. So we've now got the area of the material taken into account. That figure is 1,000 or 1.438, depending on whether you measure it in joules or kilojoules. And then it goes down. So the fibre with 8% fibre, 1,077 kilograms, 0.9, and going on down, you can see that the figures have a wider spread, the volumetric heat capacity. And now, funnily enough, all the materials fit together on the graph. So the volumetric heat capacity is a much more useful measurement. We can then take those 5 measurements, including the dense cob and the lightweight cob, and add them to known figures for a range of different construction materials. So we've got timber at the bottom of this graph. You can add various insulations that'll take you nearly down to the bottom corner. Then we got the 5 cob mixes, then we got solid clay, then concrete, then limestone, and finally steel. And again, we get this very pleasing relationship with a nice curve carrying on through all the materials, where the higher density generally leads to a higher volumetric heat capacity. There are materials that fall outside this curve quite dramatically in some cases. For instance, water has a very high volumetric heat capacity, and that's why it was used in the 70s when people were exploring the roles of passive solar heating and heat storage. Using thermal stores, they were often filled with water. But that's, again, is not part of what we're talking about today. So we were able to take some measurements of our prototype building when it was first built, and they gave us some very interesting results. So the increased thermal mass in the building can be demonstrated in this graph. This is the internal and external temperatures taken at our building during the Christmas break at the university when everything was closed. And it covers a period of about 15 days. And the internal temperature, which is the blue trace at the top, it starts off at 15 degrees because the building wasn't being heated, or it had been turned off. And over that period of time, it has only dropped by about 3 degrees. And most materials, most buildings would have got much colder, much quicker. Now, it's not particularly cold during this period. The external temperature, the orange trace, is going from about 4 degrees at the coldest point to 11 degrees. So it's not a perfect test, but it is a good example of how steady the temperature holds when you have a sufficient thermal mass. And then at the end, the temperature goes back up to 20 degrees because the heating was turned back on. So that building is performing very well. Then we had the heat wave. A heat wave, in our terms, in the UK, went up to 35 degrees C during the day. And this was during 2022. And these are the day and night temperatures during that period. So this is from the 22nd of August to the 22nd of September. And this period here within the red line is when the temperature got its highest. And the yellow trace is the external air temperature, which is going down to about 18 degrees at night and going up to 35 during the day. And the red trace is the internal temperature inside the Cobboge building, which is not going up and down, but anything like the same extent as you might expect. But also during the day, it doesn't go above 25 degrees, even when the outside temperature is 35. So it's staying cooler than the mean of those inside and outside, daytime and nighttime temperatures. So that is the role of thermal mass in terms of providing passive cooling within a building. And that is very encouraging to see. And just using the building at the time, it was clearly the coolest building on the campus, even though some of the other ones were using air conditioning to lower the temperature. So we were very excited to see that measurement. And we are generating more measurements as we speak to give more detailed analysis of the role of thermal mass in buildings. So going back to these volumetric heat capacity measurements, we also, at the request of Peter and Stephen, compared them with timbercrete. So the timbercrete has a similar density to the medium weight cob samples that we were testing, and it turns out to have a similar but slightly less of a volumetric heat capacity, but it is, within the ballpark. So again, our samples can be compared with a known quantity. And then I also did a sample resistance and U-value calculation using those medium density blocks. So again, we have internal and external surfaces. We have an internal earth plaster and a traditional lime render on the outside. And in the middle, we have a 400mm thick wall made with the 10% fiber cob with its density of 936. And adding all the resistances together, you get a total resistance of 1.56, which gives us a U value of 0.64. This would not comply with the UK, but I believe from what Peter and Stephen told me that this is useful for some of the Australian climates. So that's a 400mm wall made with a medium density cob. And what then of NatHERS? So we got a message from Peter in March last year saying that the measurements we'd completed at Plymouth had been accepted by the NatHERS steering committee. Peter again contacted us in September to say that the 3 medium densities were in the NatHERS library. And I'll leave it to Peter to explain how this works. But in fact, Peter has already given us the explanation of how this works and what it means in the context of optimizing earth walls for the NatHERS 7 stars. And this final picture is of Matt Fox and Steve Goodhue, my 2 compatriots in this study. And it's aimed to show that scientists can get their hands dirty as well. But of course, the more observant among you will realize that this is a very staged photograph and nobody's hands are dirty at all. But we did all take part in the building of this prototype building. And this is a picture of us inserting one of the moisture and temperature probes in the wall. So that piece of that black thing there that Steve is holding measures the temperature and moisture at 6 points through the depth of the wall and is giving us an invaluable range of data for research. Thank you very much. That is the end of my presentation, and I shall stop the slides. I imagine now there will be an opportunity for questions.
Jim?
I can hear you again now, yes. Yeah.
Did you hear a round of applause?
No, I didn't. No, would you like to repeat it from my poor little ego? Thank you very much.
Thanks very much, Jim. Thank you, Jim.
Hi,
We
Peter.
have some questions now. Yes, Barry?
Percentage of fibre, is it for volume or percentage of weight?
Yeah. Did you hear that question, Jim? I can answer it, but
And thank you for that. Yes. We calculated it both ways. So the figures that I quoted in the presentation of 50% fibre, that is 50% by dry weight of the soil in the clay slip. So that's not very useful when you're on site, because you don't want to have to sort of dry out your slip and measure the weight of soil in it. So we reverse engineered that to give us a volumetric measurement, which is 1 part slip to 3 parts hemp hurd. So that was what was used on site. So 1 to 3 slip to fibre. And that gave us...
That was to get your 430, was it?
Yes.
Yeah.
And we have since been working on much higher ratios or dense. So we've got down to densities now of between 200 and 250 with higher strength clays. And now it's 200% by dry weight of soil. And by volume, it's about 4.5 to 1 hemp shiv to clay slip.
So you're not having problems with mold or rotting at those very low? No? Okay, that's good.
No, there is well, we haven't taken those very low samples out into the field yet. We're just measuring them in the lab, and we're using them to make prefabricated blocks, which is the next stage of our research, is to turn that mass walling wet construction technique into a block that can be supplied to the industry.
Yeah, okay. There are other questions? Thanks, Jim. Yes, Rhiannon?
At what point does that density, when does the structure become not structural? Like when
Did you hear that question, Jim?
I think so, but if you could repeat it, Peter.
Okay, so at what point lowering the density does it not become structural?
It's a very good question, and I can't give an exact answer because we couldn't go down the route that you're going down with this medium weight cob, because that wouldn't give us the U value that we needed for our regulation. So we knew fairly early on we needed to go for this composite structure where we had a very dense cob to take the load. Those we have measured, and it has a bearing capacity that would be equivalent to a 2-story building. And I'm sorry, we haven't done a series of compressive tests on the medium weight cob, but I imagine that the 1,000 kilometers would work pretty well, and I believe it has in your experience.
I've built 1,000 kilogram density walls, and they're pretty solid. Like,
what sort of MPA do you get for that?
I haven't tested the MPA. I've just built the thing, and it was solid, and it was load bearing, and it's still there. Yeah. The other questions? Got a good opportunity here. Yes, Joe.
Checking the wall thickness on your prototype is 660 millimeters thick.
660 total thickness. Yes, that's right. When the renders are on.
Yeah.
Yes.
The dense material on the inside and the lightweight material on the outside.
Yeah, the insulating layer was on the outside to stop the weather coming in, and on the inside it was the load bearing taking the weight of the roof or upper floors, and also having that thermal mass where it could be useful on the inside. Sorry, I answered your question.
Exactly that.
Yeah. But the other overlays we have here, apart from we don't have such cold cold connections. I think Steve Dobson's just come in on his he's trying to get in on his mobile phone. I'll just let him in. What we have is bushfires. So we've got problems with bushfires. So we're try and reach BAL levels, bushfire attack levels in Australia. So and we don't have such cold weather. Tomorrow I'll talk about whether cob boughs would be suitable to Australia. I think it might work in the alpine regions of Australia, for example, maybe. But the climates here, like in the desert, the heavier the material and the thicker the wall, the better. So it's not all about insulation. It's about insulation in colder climates, and it's where we are. A lot of people have left England and became escaped the cold and came here because of the pleasant weather. Yeah, so we've got different weather climates. Any other questions?
Any tests done on the traditional cob houses in Carousel?
Oh, yeah. So that's a good question, Jim. Have there been any tests done on traditional cob houses, like I guess you're talking about the comfort in them, rather than whether they pass regulation, but how comfortable are they?
We've done real-time U-value measurements for traditional cob houses using heat flux sensors, which are discs you place on both sides of a wall of material, and it measures the flow of heat through that material. And those have given very encouraging results. In fact, my compatriot Matthew Fox lives in a cob cottage. Well, it's one that, like a lot of these old buildings, it's been adapted in different ways over time. And some of the walls are solid stone, some of the walls are cob, and some of them are made out of modern concrete block. And the insulating value of the cob was roughly equivalent to the wall built in the 90s to the building regs that we had 20 years ago, which were still fairly stringent. So cob does perform better than you'd expect. But we haven't done a full set of measurements, and that is sort of future work. That's something we want to do more of. But we know that cob works. And the whole shame of this process, in a way, you could argue that we've almost been wasting our time, because we already have a form of natural building that is proven to work, even though it doesn't measure that well. Same as you have in Australia. You feel like you're banging your head against a brick wall, literally, in order to get these things compliant. And in fact, you could build, as that chalet in the Alps showed, you can build with solid earth walls and have a very comfortable house in a lot of different climates. But we had to go through this process. And I guess cob oak building will be proven to perform better than a traditional cob building. At least I hope so.
Yeah, it will do. Yeah, regulation, I like analogies. I just feel like it's I'm a dog on a leash. The government's the owner of the dog, and he's dressed in lycra and wanting to jog along, and I'm trying to stop the doom of business, and he's just jogging along, and then and he's not really keen to pick up the end product. And that's just how I feel.
Surprised you didn't have a slide of that, Peter.
Sorry? That's right. I'd have to get a cartoonist.
Yeah.
What sort of costs is involved in using the hemp? Like, is having to use different materials for the two components, does that increase the level of cost? Is the level of cost comparable to having to change materials within the?
Yeah, I think there's a question as to the cost of the cob bouge system as compared to normal cob, I guess, or cob that's got 3 layers of 50 mil foam on the outside.
Resources, like hemp is a very
hemp's fairly expensive. Yeah.
Shouldn't be not as accessible as straw.
Yeah. In Australia, yeah. So the question, do you hear the question at all? It's from the back of the hall.
I did, yes.
Oh, you
Yes,
did.
and I can answer that from the UK point of view. Straw is very cheap. In fact, a lot of places it's a waste product from cereal crops, so you can get it for next to nothing. And that is the traditional material, but we found that we couldn't get a clay straw mix that would perform as well as the clay and hemp hurd mix.
Yeah.
Because of the nature of the hemp hurd, it's actually a cellular construction. It contains smaller and more air inside it than the straw does, so you can make a higher performing material with it. Hemp hurd is grown in the UK under license, but it is much more expensive than straw. Funnily enough, we found the cheapest source of hemp hurd in the UK was sold as horse bedding, and it was imported from the United States. So imported hemp hurd sold as horse bedding was cheaper than the locally produced hemp hurd for building.
Yeah, yeah.
Just one of those things.
Yeah, in Australia, I've looked at using both straw and hemp hurd, and the hurd is difficult to get hold of. I think I paid $1,000 a ton for it, and I think it's more than that now. But the industry is just kicking along. It's just starting up, and the processing and the harvesting is a bit of an issue, I think. And there are portable plants that are being built and made available, and the farmers are being encouraged to grow it. So I think there will be a supply down the track, but at the moment, we don't. I can get down to 1,000 kilograms pretty easily with straw or with hemp, and the hemp hurd is I was saying it's probably $1,200 a ton now, and straw, you can get jumbo bales of straw for $60 for half a ton. If you get the straw balers have pushed up the cost of straw bales a bit, and so it's easier to get the jumbo bales on the back of a ute, and you can even get them so they're shredded. It's a bit easier to deal with. Yep.
So,
any other questions?
Just a further point on that was that so by using the hemp, you're encouraging the industry, and it's a very useful material in lots of ways apart from the hemp hurd. But also, somebody asked about the thickness of the wall, and I showed. So our cobblage wall is already 600 mil thick, plus the whatever finishes you put on it. And in order for it to become more acceptable within the construction industry, we have to reduce that depth. And one of the ways we do that is by making the lightweight mix more and more efficient. So as I said, we're now down to below 250 kilos per cubic meter, and that can only be achieved with hemp hurd. I don't think you could do that with straw.
Yeah.
Can you reduce the size of the internal layer? Like, is the internal layer as thick as it is due to a structural component, or is that just? So I imagine it's the external layer that's providing all the regulation,
insulation. Yeah. Did you hear that question, Jim?
Could you
increase the thickness of the cob? Could you reduce the thickness of the cob and get more insulation? Go 400, 200 or something like that, or 250.
Yes.
That's
so what we're working on at the moment is this idea of prefabrication, where you have more control over the materials and the form of construction. And what we're looking at is to make something that's more like a stressed skin panel. So you have a thinner layer of structural cob on both sides of the wall, the inside and the outside, and the lightweight hemp clay mix goes in the middle.
Okay.
All right. We're looking at 75 mil at each, so 150 total of the structural mix, and 250 of the hemp hurd in the middle.
So you're looking at industrialization of cob.
Well, it's very hard to any sort of anything. So at the moment, cob is the preserve of the self builders.
Yeah.
And it's very hard to get it into any form of conventional construction. But one of the ways to do that is to provide it in some sort of manageable block form that's already dry, that people can just stack up and use to create the walls.
Yep.
In the block form, are you having a challenge between the light and the dense joining, like having a good bonding in a block form?
You might have to explain the zipping of it together, the mechanical sort of zipping together. Yeah, so there's the Jim will explain.
So
how the two layers
when we built our first test wall, we built it wet, as you would do. So the structural layer went in first, and then the thermal layer was added next to it. Well, both materials were still fairly wet. Then when the wall was finished and it completely dried, we needed to reduce the size of it so we could fit it into a lift. So we had to chop the end off. And in chopping the end off, we discovered that the bond between the thermal mix and the structural mix was stronger than the thermal mix itself. So in other words, it broke through the middle of the thermal mix, not on the bond. We've then done a lot of experiments with different ways of fitting the two layers together. And in fact, if you take a ready dried piece of the structural mix and a ready dried piece of the thermal mix and stick them together by wetting both the surfaces and then painting a thin layer of slip, that gives you a bond which again is as strong as each of the materials. So that hasn't been a problem. The bond is very easy to produce, and it also means therefore that the finished article could be built together using a thin bond system.
But on that, your slip, what is the, like, how many % clay to water? Like, is it like thick paint or runny, watery paint?
You have to stop being a scientist for a minute and think milk, cream, pancake batter.
Yes. Okay, pancake batter is pretty close.
Yeah.
Or cream.
Sorry.
So
sorry,
we have this might be interesting to you guys, and I don't know if you've come across this. There is a method of measuring the consistency of slip, and it's the puddle test. Are you familiar with something called the puddle test? So what you do is you take 100 milliliters of the slip and you drop it onto a piece of glass or a very flat surface from a height of 100 millimeters. So you've got 100 mil of slip dropped from 100 millimeters, and you then measure the diameter of the puddle that it forms.
Okay.
So the more thicker the slip, the smaller the diameter, and you're aiming for a diameter of 140 millimeters. And that's your ideal slip, and that has the consistency of somewhere between single and double cream or a good pancake mix.
Okay, so it's similar to a concrete sort of slump test. Similar, but not the same. Yeah. Okay, there are other questions? Good opportunity. Other questions? Yeah. David, was that a question? No. Okay. Oh, yeah. How are we going for time? I could ask some questions. I could think of some probably.
Okay, I know the question. Have you ever taken a bath in a slip?
Have you ever been tempted to take a bath in the clay slip, Jim?
Yes, we have.
Good.
Those of you who've worked with clay will know that a strong clay slip is a wonderful material. It feels sort of supernaturally smooth in your hands when you're mixing it, and if you could cover your face with it, and people do take mud baths. So yeah, the short answer is we have been tempted to take a bath in slip, but we haven't actually managed to do it yet.
Well, I've actually managed to do it.
Do you always tell the truth when you're answering questions?
That was a joke, I think.
He's a POM, so he's probably never had a bath in his life.
That's another joke. I hope you didn't hear that one.
No, it's something to do with POMs not bathing regularly.
It was.
I'm a bit I'm cold this morning and a bit peed off because I didn't get my shower first thing because my heat pump has suddenly stopped working.
That's a common problem with heat pumps.
Yeah.
So we've got any more questions? No more questions? Going.
Per length make any difference? That it's chopped in? Does that make any difference? The length?
Well, did you hear that question, Jim?
No, I didn't. No.
It's probably more related to straw than the hemp herd, but does the length of the hemp herd make a difference to the strength?
We haven't relied on any real strength qualities from the thermal mix. It is just there as an insulant, but it does affect it. The hemp herd is commercially produced and comes in lengths of about 15 mil long, 12 to 15 mil, about half an inch. When we've used straw, it works if you chop it more finely, and we've found that a clay straw mix with a straw chopped down to 50 mil is optimum. It doesn't need to be long to be strong.
Okay. That's you can buy, I think it's been through a header process in Australia. They put through the stubble, they chop it and bale it into big round bales. I've bought a bale of that. It's very, very useful, already chopped to process to work with.
When I built so before I was involved in this project, I was a straw bale builder.
Yeah.
And I built the first straw bale house I built for myself and my family 25 years ago. And in order to get chopped straw for our plaster for that project, we put straw into a dustbin and then used a weed whacker or a strimmer to chop it up. It works really quickly. You get very finely chopped straw almost immediately.
Yeah. I saw one went through I think a farmer put it through a chaffing machine or something or other, or some sort of cutting process. It was beautiful to render. Yeah. So,
yeah, we're just talking about walls, but in that little prototype, you had obviously openings. What were the lintels there, and how do you deal with the heat transfer if it's different to the wall system?
Did you hear that question, Jim?
Yes, the lintels used over the openings were made from the base of the lintel was a layer of 18 mil plywood, and then the structural elements were 100 by 50 millimeter pieces of timber, and the amount of timber and length of it was calculated by our structural engineer. But there are always going to be thermal bridges around openings. It's very hard to completely get rid of them, but we detailed them with little layers of wood fiber insulation between the timbers, as well as using our lightweight hemp mix. So we did make a satisfactory lintel using timber. You don't need anything very strong in this form of construction. There's no steel involved.
Did you measure the outcome of that?
We've measured it with thermal imaging cameras, and it doesn't show any significant thermal bridging over the windows, no.
Any other questions? Yes, one more.
I was just wondering, were there any surprises when you had a full prototype building built compared to the testing scale of the prototype? So you would build it differently with another.
So when you were building the prototype, have you learned anything from that? Have you changed things? Have you developed ways of doing it that improved since the first prototype building?
Yes. We probably learned that we can reduce the amount of the structural layer just in terms of its load-bearing capacity. We've learned how to make better thermal mixers since. But most of what we've learned is the realities of building with a wet material and the time it takes to dry. So traditional cob, the anecdotal thing is that, you know, you can work with it after a couple of months because it's firmed up, but it still has a certain amount of moisture in it. And people would tell you it takes up to a year to dry. But actually our measurements show that our building is still drying out 2.5 years after it was started. and that affects its performance. So yeah, it's wet clay or inside a building takes a long time to dry.
Yeah, I noticed that the 1000 density cob that I made with more clay in it and straw took longer to dry than the ordinary density cob that's got much less clay. The clay is the thing that's got the water in it, and the silt, sand, and gravel are inert fillers, and they don't have any water in them. So the more clay you got in it, the longer the drying time. So it's probably the thermal layer that you're going to have more problems with than the cob layer, I think, in drying time. And that's why making them into blocks is probably a good idea.
Yes, that's where we're headed, is this idea of prefabrication. I mean, cobos exists as a technique. We've got all the information on our website. We've got training videos. We've got specifications. We've got everything you need to build a cobos building on our website, but it's designed to be built wet. So the next stage is to turn it into a prefabricated building.
The beauty of the thermal side of it is that the blocks could be rather large because they're so light.
So at what point does a prefabricated cob block become a mud brick?
Yeah, did you hear that?
I did, yes. So we're in the early stages of looking at this. We're working with architects and engineers on the right methodology. And so one approach would be to have a mud brick that's a separate item from a lightweight brick, and then you combine them in different ways to make a wall. But we're also looking at a composite brick. So the brick that is the only thing you need to build your wall to comply with regulations, that, as I said, would have 75 mil of dense cob on the outside, 250 of lightweight in the middle, and then another 75 of dense on the outside. And that you would contain all you needed to make an insulated wall.
All right, so that'll go through the wall in one go.
Yes.
Okay, but the bricklayer will be going like this, heavy on one side and light on the other.
Well, the heavy bit is on each end, so it would balance.
A heavy bit on each end, sorry, and the light bit. Okay, it's balanced.
We're designing it to weigh about 20 kilos, which is can be handled manually.
Yeah, I think we try to get our bricks down a bit lower than that, because in the old days our corner bricks were about 30 kilos, which are a bit heavy, and the normal ones were about 20. And I'm not up for that anymore. Sort of, 12 or 16 kilos is good for repetitive use, but it's another thing, I guess.
It's another regulation.
Yeah, it's a regulation on.
It's got to be under 15 kilos for one person to lift.
One person lifting in Australia is
That's
now.
it. Okay. So in the UK, I believe it's under 25 for bulk materials.
Yeah. We've become so wooty. I can't believe it.
Well, I can't lift 25 kilos easily, not with my back.
Yeah. I was just going to say, what about the traditional idea that like the difference between how much straw versus not is dependent on what side, whether it's north, east, south, or west?
Yeah, well, that's an interesting. We're sort of interested in that too, but I guess the question was about the zoning of the mass, and I'll be talking about it tomorrow. Zoning of the mass to our south, which is your north. The cold side of the building, zoning a more insulated wall there, and having a heavier weight wall on the sunny side. Let's say the sunny side, the equator side, to pick up the sun and get that into the building. But on the dark and cold side, you go for a more insulated one. To play with the performance of the building like that. That was the question, I guess.
Yeah, absolutely. And if I was designing and building a house for myself now, I'd use a range of different materials at different densities according to the solar orientation.
Yeah, that's right.
One of our partners in the project was a French architect called Francois Strief, and he built his own house. And the north wall and the west and east wall, which are the colder walls, he built out of straw bales. And then the south wall, the one facing the sun, was made out of round earth behind glass.
Yeah,
So the whole of the front of his house was a passive solar sun space.
Yeah. I think there's more to all of this than just the U or R value of the external walls. It's about design, really, clever design, good design, and design for climate, appropriate to climate. So that's what this whole thing's about. But
and how often do you see that in modern architecture?
Well, you don't. It's in the NCC, the National Construction Code 2022 performance guide. It's a performance standard or a performance guide. It says if you have a 7-star rated envelope efficient walling system house and a Gen star rated air conditioner, a good one, decent efficient one, fully ducted one. That's the solution for every climate of Australia. So that's sort of what the government, the bloke with the lead, is telling us to do. And I totally don't agree with it, but he's got the lead. I'm just the dog. Is there any more questions before we have beer?
Don't shit in the house.
Okay. No more questions? Okay, I think we might thank
Yeah.
You heard that, but you've already got our eternal gratitude, but that's just a little clapping as well. So, thanks, Jim, and we'll talk again.
Thank you all, Peter.
Hopefully, we'll talk again.
Thank you, Stephen, if you can hear me.
I think he's on there, but he's possibly muted.
Yeah.
Okay.
Thanks, Jimbo.
Okay. Yes. Okay. Thanks, Jim. We'll see you another time.
I'll leave you now. Thank you.
Okay. Bye-bye. Thanks, Andrew. That went well. It's always a bit of a worry. Okay. I think I'm going to have a beer. So, thank you, everyone.
All right, welcome back, everyone. I don't know about you, but I'm really thankful for today's weather, especially after all that hard work we did in the morning. So good on us. So this talk is going to be recorded, the talk and the Q&A. So our topic now is on the NCC update with regard to passive low energy assessment, particularly highlighting some of the problems with the NCC 2022, including outdated climate files, danger of the assumed reliance on air conditioning, and future-proofing of homes for a warmer climate, and the need for an assessment pathway for passive low-energy homes. Now, this talk is being brought to us by Marci Webster-Mannison. She's joining us from Brisbane today. Just a background on Marci. Marci is an ecologically inspired architect with over 30 years of experience. She works with Melbourne Design Studios servicing Queensland and New South Wales, especially specializing in institutional, sustainable and cost-effective architecture. She's a recipient of a special jury award for ecologically inspired architecture, and her projects have won over 25 design awards at local, state, national and international levels. One of her best-known projects is the Charles Sturt University, the Thurgoona Campus, and it's a model for environmentally sensitive yet cost-effective design practice. We had our international conference there a couple of years ago. It's a beautiful campus, lots of round earth buildings and buildings using recycled timber and conditioned by unique passive solar heating and cooling systems. and Marci has been a very special member of our EBAA committee since 2016. So over to you, Marci.
Thank you, Susan, and apologies for not being able to join you in person. I'm delivering this talk from Yugara, Bull, Yugara, Jagara, and Turboland. Human-made materials like concrete, metal, plastic, bricks, and asphalt now outweigh the entire mass of living matter on this planet. The amount of plastic alone is greater than all of us, more than the mass of all land animals and marine creatures combined. As the planet warms, the technology that people use to stay cool is making the climate hotter. Half the world's population face extreme heat this summer, and about 3 billion of these people did not have air conditioning or any access to cooling. People are dying. In India alone, 630,000 people died last year from high temperatures. Yet cooling accounts for a fifth of the electricity used in buildings. That is 10% of all global electricity consumption is used by the richest and the coolest countries. Additionally, the refrigerants used are themselves a deadly greenhouse gas. Some 46 million health professionals called on COP28 to immediately phase out fossil fuels. This is the future we don't want. We are at the tipping point of our collective future. In the face of climate chaos, ecological collapse, and species extinction, will we keep cranking up the aircon as we watch the planet burn? Simply put, yes, we do keep cranking up the aircon. The basic premise of the new energy efficiency provisions of the National Construction Code, NCC 2022, is that all new homes will be air conditioned. The NCC 2022 requires a new minimum thermal performance rating of 7 stars under the nationwide House Energy Rating Scheme, NatHERS, and all new homes must not exceed a legislated annual energy use budget. Annual energy use is calculated assuming that the home is air conditioned 24/7 and based on a mandated allowable minimum and maximum temperature that sit in a very narrow range. And that's to determine when the air conditioning kicks in. This short update will highlight some of the problems with the NCC 2022, including the outdated climate files and the lack of consideration of future-proofing homes for a warming climate, and the dangers of assumed reliance on air conditioning in determining compliance, and the need for an assessment pathway for passive low-energy homes. The last thing we need is more stuff. So why mandate damp, dark, poorly ventilated, multi-skilled homes that mold loves? Then add in all sorts of expensive construction and mechanical equipment to try to make these places livable. Well, livable that is when the electricity's on. A key problem is that the climate files used to estimate the air conditioning needs of a home are decades out of date. The code ignores the fact that our climate is warming and that over the life of a building, 20, 30, 50, 70 years, the external conditions will change to a large extent. This is how bizarre the situation is. Based on CSIRO climate predictions and the new energy provisions of the NCC, if we were to design a home to suit 2050, we would actually not be allowed to build it now, even though that house would use significantly less energy for cooling in our climate of 2020. Basically, we are not allowed to design homes that are future ready, that can keep people safe and reduce electricity bills. the assumption that incorporation of mechanical heating, ventilation, and air conditioning is inevitable leads to some radically different decision-making about the building's form, the layout, construction, and landscaping, and its priority is given to climate-appropriate design. The other big problem with the new code is that the performance of homes is assessed assuming that the home is air conditioned and that the air conditioner is on. Modelling of homes in Western Sydney shows that code compliant homes become unsafe when the air conditioning is turned off. So these homes are dangerous in heatwave induced blackouts or when air conditioning is unaffordable. Reliance on aircon puts unnecessary pressure on our power grid, leaving cities vulnerable to energy failure. Furthermore, not everyone can afford to use aircon. So what are we saying about equity in this country? The safest and lowest energy option is to build a climate responsible home that uses little or no energy for heating and cooling. Yet the NCC makes this virtually impossible. Avoiding air conditioning should be considered best practice by NCC. The safest and lowest energy option is to build a home that uses little or no energy for heating and cooling and that will be more resilient to extreme climate conditions and blackouts. EBAA has been intensively lobbying the NatHERS team, and the NatHERS team has agreed to look at an alternative assessment pathway for passive low-energy buildings, which may include adoption of an appropriate adaptive comfort model and the use of NatHERS in free running mode. An adaptive comfort model takes into account how people interact with buildings. So considers things like what clothing is worn, what windows are open, are the shades down. Interestingly, research shows that buildings that are designed for adaptive comfort are actually considered more comfortable by occupants than buildings relying on air conditioning, even in the same temperature conditions. NatHERS is a predictive modelling tool for thermal performance, used to demonstrate energy efficiency compliance with the National Construction Code, the NCC. The home is rated based on the amount of air conditioning, heating, or cooling that is predicted to be needed to keep the home within a set comfortable range. This set range is legislated and does not recognise adaptive thermal comfort or how people can operate a home. And it uses thermal comfort set points that favour highly insulated, sealed up buildings. NatHERS energy rating discriminates against the application of climate responsive design, such as heavy rate rammed earth homes or lightweight, naturally ventilated homes. NatHERS used in regulation mode, which is what's required for building approval, does not suit low energy homes, passive homes, or for that matter, existing vernacular homes. NatHERS can't handle the behavior of occupants, natural, stack assisted, or mass link ventilation, or radiant cooling, or humidity, or the way different materials store and release heat. NatHERS in free running mode, which is not allowed for certification, it does attempt to model how homes respond naturally to the climate, but currently it can't be used. And it's also fairly limited in terms of what can be modeled. The NCC focuses on R value, which is resistance to heat flow. So insulation has a high R value, which is relevant to lightweight construction and with insulation. But thermal capacity, which is the ability of the material to store the heat, which is an advantage to earth construction, is ignored completely. The high thermal capacity of earth construction can reduce the heat flow from the outside to the inside by storing heat in the earth walls, slowing the heat flow from one side of the wall to the other. That helps keep the temperature in the home stable. Due to the relatively low thermal resistance of earth building materials, that R value, it's very difficult to comply with NCC. EBAA has been working with Cobbage and the University of Plymouth's Environmental Building Group to establish the density values for lower earth construction materials. The NatHERS team has accepted these new values. The NatHERS material library now includes varying densities of earth wall construction and their thermal properties. Such newly accepted lower density values can be achieved by using earth wall building techniques of lower density rammed earth, mud brick, cob, daub, and light earth. We are also contributing to the NatHERS technical note and handbook. Complicating all this is the massive lack of monitoring of how buildings actually perform. Models, after all, are imperfect representations of the real world, and the results are only relevant within that closed world of the model itself. It is ridiculous that modeling is being used as a regulatory tool without being suitably tested in the real world. The NCC paints a scenario of reliance on guilt-free air conditioning powered by renewable energy. This doesn't address the impacts of air conditioning, peak load demand, the global warming potential of refrigerants, or the safety of occupants in heat waves and bushfires when power is lost. It doesn't resolve the negative relationship between indoor air quality and energy efficiency. It doesn't consider embodied energy or climate change resilience, or whether designs assist rather than hinder the transition to renewable economies. It doesn't respect the most vulnerable of us. Thank you.
Thanks, Marci. That was great. Right. Oh, yeah, good. Thank you. Yeah. I don't know what introduction means, David, but anyway, to put everything, I'll just next slide on that. Put everything in I've been working towards into perspective. I totally believe that passive low energy earth architecture, which is what PLEA means, is the only way the world can provide anyone and everyone anywhere with safe, healthy, comfortable, affordable and desirable buildings using one's world's resources. As we witness the impacts of climate change, as we observe populous developing countries trying to live as wealthy countries do, as we start to consider embodied energy and as we transition to renewable energy, it will become more and more obvious. We need to return to what has always been sustainable, what is simple and what works. Earth building needs to be ready to rise to this extraordinary challenge. It is completely feasible because it has been done. It's been done for 10,000 years. It's proven. Rammed earth is going gangbusters in million-dollar homes and multi-million-dollar commercial projects of extraordinary beauty. Earth building needs to pick up its own build and mainstream affordable homes and passive low energy homes, and NatHERS compliance has been the hurdle. So this is the sort of building that Marci loves, I love. It's just a simple building in China that won World Building of the Year award. just a rural building. This one here is the social housing in France, built in the 1990s. You know, why not this sort of thing in suburbia? So last night I discussed two momentous successes for EBAA, and for those who missed last night, all the talks will be online pretty soon. The two successes were the inclusion of lower density earth materials that allows optimization of earth material density for climate, and the alternative pathway of assessment that is in the works program at NatHERS, and Marci's talk has just discussed that. So I hope both great leaps will resolve thermal assessment hurdle, and we can get on with promotion, education and research. So this presentation is loosely based upon what I've been putting together over the recent months for NatHERS. It goes, before it goes to the NatHERS, I'm sharing the fuller version here. The following is information that may help designers and energy assessors understand the benefits in utilising passive low energy earth architecture. It is especially useful for those interested in helping clients meet NatHERS 7 stars performance through taking advantage of the newly introduced lower density earth materials through optimising thermal characteristics for climate. What follows is limited information and guidance based upon some modelling and experience of vernacular earth building developed around the world appropriate to climate. So it's a bit of a chicken and egg situation. We only just got the things into the library, so not much modelling has been done, but we can look around the world for clues and cues on what's a good idea or not. And I'll have a bit of a crack at that later. So it's a different approach to what has been encouraged in Australia due to what appears to have been a response to improving what is a dominant mainstream reality rather than striving for best sustainable practice or considering a more holistic solution. So I think Marci's covered the problems with the status quo. So I might just skip the next two things, but I can quickly go through it. You've got energy efficiency versus poor indoor air quality. Either got a sealed up insulated box with an air conditioner going efficiently, or you open the windows up for fresh air and you lose that efficiency. Condensation, interstitial and surface are a problem. Poor summer performance is a problem. There's a performance gap in cooling. The higher the star ratings, the worse the building performs in summer. Peak load demand means price of energy is up and transition to renewable is more challenging. You've got the heat island effect and noise from air conditioning in cities and towns. You've got high embodied energy of new buildings. The higher embodied energy is you put more double glazing, insulation, membranes, everything you put into buildings without considering them is maybe pushing up the energy that goes into buildings more than we're saving on having more efficient buildings. No one's looking at it. Short life of buildings and then toxic landfill as they get demolished and they're too hard to disassemble, so they just go to the tip in one piece with lots of things in them like foams and stuff that you can't recycle. You have to bury it. So today's best refrigerants are so I've covered pretty much all this. I think Marci's covered this. So I think I might just move on. So there's 69 climates in the NatHERS system. I'll just get up to where I'll skip all that. Yes, I'll find it where I'm up there, sorry. Okay. The 69, and they're roughly your postcode is considered to be a climate file. For example, my That's my climate zone is 18. Postcode is 2541, which is in the Jervis Bay sort of area. That's Jervis Bay there, so Jervis Bay, so I live there. And so that area there is one climate file. There'd be another one similar somewhere else, another postcode that's a similar climate. But the thing is that where the weather station is can change everything. I think the weather station that we're using is actually inland in Nowra on the coast, so it's a bit different. So if you go into NatHERS and you look at online at my climate, you'll have all this information, which is basically what's in the climate files. And NatHERS regulation mode or in free running mode will look at the climate file and it'll sort of do billions of calculations, a massive computer, and apply temperatures to the building night and day and try and work out how the building might operate based on that. So that one there is the temperatures, minimums, the maximums, the really, really high ones, the normal ones. Some are, and over on the right-hand side, you've got averages for the different seasons. And here we've got the moisture in grams of moisture in the air, like humidity, and global solar, which is your sunshine. So you can have a look at these if you wanted to, but then there's wind direction, wind strength. So they're all factored into it. So it's probably easier to not talk about 69 climate zones. It's easier to talk about 8 climate zones and try and understand what you might do in those climate zones. So I've picked the NCC, the National Construction Code climate zones. There's 8 of those in total, and I'll go through these and I'll look at what I'd sort of think you might do in that climate zone. So I've lived in 6, I've lived in 5, I've lived in lived in Queensland, I've lived in Northern Territory for a while, so I've got an idea of what it's like to live in some of these climates, and I've worked and lived in a house in the Philippines for a while, which is similar to some of these climates too. So I've lived in a few of these climates, but not all of them. So that one there is that's the green one, so it's here, down there, and it's above me, Wollongong up to mid coast sort of thing, and that's the Goldilocks sort of climate zone. The Mediterranean, temperate and subtropical climates in there, and I think the way you look at buildings is in hazards and lifestyle as consideration that sort of no one really considers. You don't just plonk a brick veneer house of the same design in every single capital city of Australia in any orientation. If there's enough insulation and sealing in it, it works. I don't believe in that. That's just silly. So you should look at that. You should look at the lifestyle that people want to have in that climate and build a house that suits that, not one that's going to be efficient for an air conditioner running. So that's the sort of, in that Goldilocks climate, you've got these earth walls, standard sort of thickness of mud brick or rammed earth, and a little bit thicker, and those ordinary sort of weights of mud brick and rammed earth, and even maybe cob sort of density, with thermal mass as the driver for the mass link ventilation, reflective and bulk insulation, medium coloured roof, passive solar design orientation, sort of basic passive solar design, which are these things here, maximising the glass to the north, east and west orientation, minimising east and west sun single glazing, low air glass. Yeah, tall ceilings. So we've lost tall ceilings. We've gone for 2.4 because that's the width of a truck on the road, and that's a problem in buildings, all modern buildings, I think. On ground without insulation, I'd say. And you've got to look at the sun angles because there's quite a little bit of latitude difference in those green. There's even green up here too. So, and deciduous vegetation. These are up for debate too later, but this is what I'm thinking. But so climate zone 2 is the yellow. So that's this area here from I don't know where that is, Yamba or even further south on the
Coughs, I reckon.
Coughs, okay. Coughs and up to what, Rockhampton or somewhere, or no,
Yeah,
Townsville or something, or whatever. Yeah.
Over inclusive, but yeah, I think that's what it says.
That's probably Capricornish area. So you know, what are the hazards there? You got storms, flooding, cyclones, termites, insects, high humidity, and then you've got lifestyle. People want to live outdoors. It's possible to do so all the year. A fair bit of rain and humidity and insects and crops and stingers and all sorts of other things. But so the standard thickness should work up there as well, but you don't do passive soil design up there. You're starting to look at the tropical design principles, which is shade, shade, shade in vegetation and in the design. Tall ceilings, definitely tall ceilings. Less compact design to facilitate cross-flow ventilation, ceiling fans, maximise ventilation with louver windows, shaded and insulated outdoor living areas with fans and screens. So people want to live outside, sleep outs, veranda sleep outs. I remember, veranda sleep outs in Queensland with louvers all around. Pleasant out there. Zoning of the mass, so the heaviness of the building is better if it's in daytime areas. If it's in nighttime areas, you can't sleep at night, but if it's in daytime area, it's an advantage there. That's what I've found in the Philippines. And then the mass needs to be shaded. But the mass, this is sort of going back to what the problems are. You've got a good hold down for cyclones and rigidity, and then there's less flying objects when you've got massive buildings, and you've got protection. Like if sheets of iron are flying through the air, I'd rather be behind a massive wall. I noticed one thing in the Philippines too, that I didn't think people would want mass buildings in the Philippines. When I asked to go there to do low cost housing, I thought that's probably a bit silly. So I looked up the design principles, and mass was a good idea in a book I read. When I got there, people were getting really cold. If a storm had come over and it was raining, and they'd be freezing, they'd be chattering their teeth and freezing. So, we've got funny expectations when we don't live in places. So 3 and 4. This orange and light yellow. It's a fair mass of Australia, but there's
most of the continent.
Yeah, hardly anyone lives there. But David and Sherry and I were in this neck of the woods here a while, and they had mud brick houses there, and very comfortable. Building next door to me was a bachelor education centre, which was concrete block on a concrete slab. And it was a very comfortable building with the windows open. It was a nice building to be in, but the domness that we were living in was shocking. Like the air conditioner was on in the morning, trying to warm you up in winter. At lunchtime, it'd be flat. Someone would get in there, get up early, and they put the air conditioner on 28 degrees in the morning because that's as high as it could go. And by lunchtime, they put it down to 16 because that's as low as it could go. And it was just a yo-yo sort of air conditioning situation in your tail all day. So the hazards in that area are extreme heat and freezing cold nights with very low humidity and potential dust storms. The winds change. You've got to work out where the winds are coming from. That's why the files are useful. you've got to have mass. Mass is the king in these climates, and that was shown by a PhD research student at Adelaide, South Australia University, University of Adelaide, Zhang Dong, and he found that the heavier the walls, the thicker the walls, the more comfortable, and putting insulation in was a waste of time. So that's what I've got written up there. If you just think about the Birdsville Hotel, you think about the hospital in Alice Springs, the telegraph station, all those old public buildings that were built over 100 years ago, and they're still comfortable in summer, and modern buildings aren't out there. So we've just lost the plot as far as designs go, because we've got the old, the solution to all bad building designs, the air conditioner. So we've just given up on it. So that's where the whole country. I was just driving every time I went from Alice Springs to Utopia. I was just looking around saying, God, you could build Sydney, Melbourne, Adelaide just out of the dirt on Utopia easily. There'd be plenty left over. It's just perfect for building. So, these are the things you need: shaded verandas and outdoor workspaces. When I was in Iran, there's just so many good ideas with their designs that go back, 1,000 years with courtyard designs, and the Baghdadis. I did a presentation on that in 2019, coming back from Iran, and the reflection pools in the middle of the courtyards because they've got desert storms there too, and winter sun spaces. So there's a huge range of sun angles to consider in there. So it's hard to say it's just two zones. There's lots to consider there. But shutters, breeze walls, good ventilation, especially for nighttime purging, tall ceilings again, and evaporative cooling. That's the thing you need in that climate. You don't want an air conditioner, a reverse cycle air conditioner out there, because it's already dry enough and the air is dry enough. But evaporative cooling, actually putting moisture into the building, and it works well with mass link ventilation. You do the same things at the same time. So it's putting moisture in and cooling the building down. And then, of course, underground living is a potential thing, as it is in Cooper Pedy. So the zone 1 up here, cyclones, huge potential for cyclones, huge problems with ants, crocs, I think everything really. But extreme humidity, build-ups were uncomfortable. Flooding, rainstorms. So you need a lot of shelter from heavy rain for periods of rain, and you probably need some raised platforms and things like that to get out of it. Now I've used 1600 in the Philippines. I reckon it'll probably work up there. But these ones will too, as long as you. I'm suspecting they will. I'd suggest you model this, and I think that'll work. You've got to shade it. It's got to be all shaded, totally shaded. The building's got to be shaded. Vegetation. Orientation is not to the sun, it's to the breezes. So it's a different. This is from the book I read on tropical design, which I found very effective. The Philippines, we had unlike here, there was tall mountains, and there was always a coastal breeze going up the mountains until 4 o'clock. The breeze would stop, and then they come back down the other way. So it's predictable. So you've got to know these sort of local things about the climate and use those to your advantage. So shaded mass and the mass zone to daytime areas, mass on ground. You've got to consider the bit of freeboard on the building in case there's flooding around, and that mass gives you good protection from the cyclones and the storms. In storms, the temperature can change dramatically. Everything changes, and it's good to have a bit of balance in the building. And then some maybe raised sleeping areas, so sleeping in lightweight sort of situation at night. Tall ceilings, open spaces, cross-blade ventilation, ceiling fans, louver windows give the best ventilation. It's 100%, 99. Lose the thickness of the blade. light coloured reflective roof and reflective insulation and potentially fly roofs. 6 and 7. So this is blue, light blue, and the darker blue, and that's my climate. I'm about there somewhere, just east of Canberra, and so we've got bushfires, heat waves, cold snaps, climate change to consider. Indoor or conservatory in the winter, because it goes right down to Melbourne. Outdoor living, other seasons. So I'd probably live outdoor most of the year where I am, but it's considered the same. But it would be nice behind a bit of glass or something like that, just a bit of protection in the winter. So here you're not looking at passive solar. When I started looking at passive solar in the 80s, it was America had active solar, which is a sort of passive solar with a few additions to heat in winter. So conservatories, rooftop space heater, which I've got, trom walls, good roof insulation, good thick insulation and bulk and reflective. So this mass you can still use insulated, or maybe you might consider getting it down to this. If it was rammed earth, getting it down to that maybe, or this with mud brick and cob, or you can do thinner walls with the light earth. Mass link ventilation is still important. Nighttime clothing is still important. It gets very, very hot down there. Like heat waves in Victoria, they're worse heat waves than we've got up where we are. So these are the challenging climates for NatHERS compliance at the moment, and I'll show you in a minute the modelling that was done that shows that I can get my house up to 7.4 stars and build it again if I had to. So it's interesting looking at my house. I know so much about it. So they're the things I talked about. Climate change resilience is important. The modelling I've done on my house here says that in 30 years it'll have a climate like there, and in 50 years it'll have a climate like there, and 70 years the climate will be like about there. So you've got to consider that in a house that might last 100 years. Okay, so so it's just basic passive solar still. East-west long axis. You've got to look at the sun angles. So you cut out the sun in summer, but you let it right in winter. On ground, possibly under slab, and definitely edge slab insulation, not foam. And maybe hydronic heating. Compact design, loft bedrooms, 2-story, ski and sofa. Getting the sun right into the building as far as possible. Earth berming for keeping the south warm. Low air glass, double glazing, depending on where you are. Deciduous trees and vines, so you get the summer shading and not adding to the bushfires, but you also get full sun in the winter. So that's what Tony Isaacs, he does contracts for NatHERS. He is a sort of a well-established, well-recognised energy rater, and he has Activate, which is one of the tools that you can play with more. It's hard to load, but there's more you can do with it, I think. So he's got my house was 3.1, 3.2, 3.3. It's changed a little bit with the versions, but very low star rating because it's an old house. He said, "Oh, yeah, that's good for them, for that era." But it's a house that also is beyond carbon neutral. It's 113% carbon neutral. It's a full life cycle design. It's climate change resilient model for that. It gets 10 stars out of 10 stars in the scorecard, the new scorecard thing coming out. 6 stars out of 6 stars in neighbours. Costs less than $1,000 to run a year. So there's not much wrong with it, but that's the problem with it. But I said to him, okay, if I want to build that now, the pathway is not in, how do I do it? So he said, okay, I'll leave everything as it is, double glazing the clear story, which I've already got. You know, put in the sort of insulation that I put in the houses now because I have to anyway. So it's R3, so it's, you know, like 190 mil bat and anti-con as well, which is my usual practice. Gets it up a little bit. Weather strips, and also putting on like fresh air, but you can always open the window. You just have to do it for compliance. And when I built the place, I didn't have enough money for more glass, so I agree that it could have done with more glass. So it only gets up to 4.4 stars doing all that. So that's some of these things I don't agree with. He's done about 20 iterations of this. So he went straight to 1,000 kilograms. I thought that might get me 7 stars, but it didn't. But it gave a great jump to 5.7. If I did thermally improved windows with low E glass, it's getting up there around 6 stars. If I did that with change to light earth, which is it's a funny thing to do, I wouldn't do that, but it gets 6.3. Double glazing, goes up a little bit more. Waffle pod, there's no one going to do that. Because a friend of mine does demolitions. We couldn't take a waffle pod slab anywhere but to the tip and bury it because it was toxic. They couldn't recycle concrete anymore, so they had to load it in the truck and pay a fortune to get rid of it. So there's all these variations, and these are probably the ones I might accept. I don't really want to put anything under the slab because I'm looking ahead to, well, I'm probably looking at 20 years optimistically. But anyway, I'd like the house to be able to work well into the future when I'm in the ground, sort of thing. But I wouldn't use foam, but I could use perlite, I could use clinker or something like that, or foam glass if it's available. If I went to 1600, I'm getting up to 6.6, ever so close. But what he's done is taken out a bunch of these things here. So if I stuck to that, maybe ignored that, went down to 1,000, which I could be happy enough with, or 1,600, very close. Double glazing might have got me there, I reckon. So it's me accepting what I'm willing to accept, not what he felt I have to have. But anyway, so we'll move on there. So this is the Alpine climate, white there, a little tiny bit up here, I think, and down in Tassie. And that's outdoor a lot of the year. So these are the snowstorms, extreme cold, the heat, bushfire risk, broken bones, especially if you're going down a slope and hit a tree or something like that. So the outdoor, a lot of the year, even the very bright sunny days. So it's even in winter, the nights are freezing, but the days are nice and sunny. They can get a lot of sun into the building. So that's a tough one. That's a really tough one for compliance due to there's going to be a predicted heating load. It's massive. So I reckon that one, the darker walls really help in that sort of climate. But mass is still really important. If you get a whole heap of bodies just come into the room, all sweaty after skiing and just like all these people in this room, you need to have that mass. You need to and control that humidity. So cob beige might be a good system there, or insulated heavy stuff. So that's on ground. You have to be insulated under the slab and edges. Hydronic heating, probably a good idea. Double glazing, excellent bulk and spec insulation. And then potential to use all those things that can add extra, conservatories and rooftop space heaters. Yeah, and skylights, Velux skylights. They use them in Europe a lot, and they can be shaded. They'd overheat in a lot of climates, but up there, it'd be probably worth looking at them in Australia. Deciduous, you can't really get much growing in this class up in the high Alps. But so these are the things we looked at yesterday. We don't need to go through that again. So the density calculations, NatHERS wanted us to be able to prove to inspectors that we've got the right density. So I'll leave that up there, so you can go to that if you need to. But it's pretty obvious that you measure the volume and work out what part of a cubic meter that is, and then multiply it by the weight. So that's how we put it. It's not how it is in the climate in the NatHERS library, but it's probably a nicer way of putting it. So where to from here? So we're still chasing the appropriate pathway for passive low energy buildings. We won't give up on that one. At the moment, as I said before, it's a chicken and egg. We haven't been modelling, so we don't know. So we've got to get some modelling going. But EBAA is here. We're going to try and converse with designers and assessors and get feedback, and we want to come up with a bunch of principles like the ones I tried to put up there, just brainstorming myself, for each of the climates, design principles for good design in each climate. So part of that, we're putting together we talked about this last year, and then the conference came along, so we get sidetracked on that. But we're thinking of putting together a competition, and quite a few universities, including people here, are interested in that idea. And I know Susan was interested in opening up to professionals as well, for architects. That's worthwhile looking at too. So we're going to set the metrics for that ourselves, and work out how we judge it. We'll probably have to stick with 7-star compliance as a bare minimum, but safety, health, climate change resilience, embodied energy, all these sorts of things that we can put in there, because it's our standard, not anyone else's. So we can shoot as high as we want with it, and try and educate people on what's important as well doing it. So so once we do that, we're going to pass on that. Well, the whole process will be about passing on the knowledge we gather for good passive low energy earth architecture, and we'll share that with the government and online and through Facebook and so on. So and that's what we're trying to do. Get a really good high performance sailing boat. Sorry to use a slide last night and tonight, but I like that. Oh yeah, that's it. So I think Marci and I can answer some questions.
What was the chicken and egg again?
Well, we've got the low density material, lower density materials into the library. So there hasn't been any modelling done. Very little modelling is being done to check that they will work in what climate and what thickness, and But
well, that's the egg, really, isn't it?
Yeah. Well,
we hope to grow the chook from there.
That's right.
Could I just ask a question while you're lining up the microphone?
Yeah, sure, Steve.
I think you should write a book on this, Peter. You've given it a lot of thought, and it's very involved, but people really need to be better aware of this. And while we're waiting for an alternate pathway, modelling and predicting the output for thermal mass, we had those rammed earth houses in Kalgoorlie, which were designed and very successful, but the only way to model them as thermal mass was very expensive, whereas NatHERS is simple and cheap. So I think anyone interested in modelling thermal mass houses to show that they are comfortable using adaptive comfort criteria should speak out, because I see this as something that we can do in the interim if we can find people who will do this modelling and publicise it for the benefit of earth buildings. It's more of a comment than a question. Thank you.
Steve, I've got a day job, mate. I can't write a book. I think we're about 15 minutes behind, but I think we've got time for 15 minutes of questions, have we? Hayden.
I noticed when your friend did the NatHERS modelling that putting clinker under the slab made a fairly big difference.
Yep.
Is that something that they've got in there?
It is.
They've got that. They can go this under the slab.
He said that Ryan should put clinker into NatHERS. I think he might have sort of looked at clinker's figures and said, "Oh, that's the same as putting in something else that was in there." And flat.
Yes.
But under slab insulation, they're fond of.
Yeah.
When I started out, they were talking about ground coupling as being important in passive solar design. Coupling to the ground, you've got all that cool in the ground, that moderation in the ground. You want to be coupled to it. And now they're talking about decoupling from it because you've got an air conditioner.
Oh, genius.
Yeah. So I'm not keen for that one in my climate.
Yeah, I'm not either, but keen on getting things to the computer program.
If you're up in the Pilbara and you're living on iron ore, it's pretty hot underground. It just radiates right under the building. So you've got to separate. And there's places where it's freezing cold. You might want to separate. But I wouldn't do that. Did you hear that question, Marci? Would you like to?
Yeah, I think this turnaround with the coupling of to the earth is just another example of people that making these regulations that don't really understand how buildings operate. And just because the model tells you something, the model, as I pointed out, is limited. We cannot model all the things in the physical world. It's just not possible. There's too many factors, as we see with climate change. So this obsession with modeling something, when I come back to that point about monitoring, that we should be out there monitoring buildings that are actually working and then draw conclusions from that. If we have to model it, adjust our models to suit the real world. But I'm a bit skeptical of being able to model anything in the real world accurately.
Hi, Peter, it's Ryan here. Do you mind if I just jump in there?
Yeah, go on, Ryan. Yeah.
Hi, everyone.
Welcome.
Thank you. Thanks for having me. We've done a fair bit of work around this coupling or not coupling to the ground with both our architecture practice and with clinker. And what we've found through, I know there's limitations to modelling, Marci, but it's a starting point before you build a whole building. But then when we put it into practice and test things, what we're finding seems to be a good solution is it's a rule of thumb really, but in areas where you're more likely to have summer cooling load rather than a winter heating load. So for instance, hot climates coupled to the ground is a good idea. We still think that insulating the slab edge in those climates is good, but coupling to the ground is good where it's hot, sort of anywhere, more or less everywhere, even in Victoria, and except perhaps the hills around Melbourne and alpine areas. And then in Tasmania, we're more or less insulating in the cooler areas where we're insulating or recommending to insulate under the slab and also the slab edge. So it's about the temperature of the soil and what you're trying to achieve inside the building. It's also on a case-by-case basis because not all buildings have got the opportunity for great passive solar design. So if they're very, very cold all the time or very, very hot all the time, you can use the coupled or non-coupled slab to your advantage.
Yep.
Yeah, that all makes sense, Ryan.
Yeah, it's a good thing to have modelling, but it's when the computer says no or yes, rather than give you feedback, good, useful feedback, it's a bit of a problem. But
One of the
And then
things
there's car ban criteria, there's all sorts of other issues, but yeah.
one of the things that was very frustrating with the modelling is that sometimes it doesn't give you the benefit when you're doing something that's obviously positive, like insulating the slab edge. There was many years when we were going to great lengths to do that and deal with thermal issues and detailing issues, but the modelling software wouldn't give you the benefit. But you know, in practice, it works well in most climates.
Okay, we got some more questions, Dave.
Just about clinker.
Yep.
The only other time I've ever heard that name is in steel, steel manufacture. Is this the same thing?
No, I'll be talking about that and giving you a bit of background about the product clinker when I talk a bit later on. But our clinker is a trade name, not a standard name. But there are a number of different industrial materials that are somewhat known as clinker. But yeah, our product is a product name, and it's based on clay.
Yeah.
Okay, so that should have been a question to Ryan after this.
Just got a question on the electricity usage aside from air conditioning, which is of course very wise to do. But how does that go with everyone buying EV vehicles, which are something like 4 times the electricity usage of an air conditioner?
Yeah, so it's sort of a little bit off topic, but I think I'll answer it though. Yeah.
I'd be happy to answer that. I mean,
Okay,
it's a really good point. And I mean, it comes back to my introduction. We just can't keep creating all this stuff. It doesn't make any sense. I had some friends that did this is their area. They did a life cycle costing of running an old petrol guzzler, taking into account pollution and everything, compared to buying a new electric car. And it came out better ecologically, environmentally, to keep running their old petrol guzzler. Because, I mean, the amount of energy...
Wrong.
The amount of energy that goes, it's the same with solar power. We cannot produce the amount of panels that we would need to power the world globally.
When fossil fuels
in an ecological manner, it's the same with electric cars. We have to stop adding to more stuff. We cannot have private vehicles continuing as our main form of transport. It needs to be banned. And we have to face up to these sorts of extreme lifestyle changes that will be necessary if we're serious about combating the climate chaos that we are facing.
Okay, no curly ones, please. Anything to do with related to the building.
I've got a more realistic one. Peter, I think your lightweight bricks will ultimately improve the R rating of the building. Probably coupled with an air gap between like a cavity brick. But do you think this is at the expense of the load bearing? So.
Well, yeah, I won't be doing cavities in mine because I like doing load-bearing walls. And I don't want to produce cavities in there and leave them out in the rain while I'm building them when I'm building with earth. I like a fully sealed off wall all the way up. So I won't be doing cavities. That's why I'm looking at lower density instead of cavities. Okay, so well, maybe one more question.
Just a real quick one. Were you using a temperature gun?
I was.
Yeah, I was quite right. I don't know if you're going to notice that, but
What about Martin?
the question is, you know, there was some talk there about heavier and thicker walls were better in the zone that currently designed this. And then you said there's ongoing testing, there's ongoing pathways being opened up. You may have answered this, but you know, how long until these pathways for these kind of thicker walls and stuff?
Okay,
and what do we need to do to get there?
Well, you're in Deniliquin, which is in New South Wales, so you might be able to use BASIC's thermal comfort, thermal DIY assessment tool, which is easier than NatHERS.
Not anymore.
Well, we don't know yet.
I think because we're over 500
100 square meters, we
Yeah.
need more.
Oh, okay, right, okay, okay. If it's a big one, then, okay.
Yeah, you're not in the.
So right, yeah, out of that. Okay, but when I said there's limited modelling being done, there was a PhD research project done using NatHERS tools that said that climate should work. That's what I'm basing that my assumption that the thicker and heavier weight buildings will work in that climate.
Dry climate.
Yeah. So have you had modelling done?
No, we've started.
Or we're just afraid?
Yeah, we've got the, it's in the pipeline.
Yeah, okay. Oh yeah, if it's a huge project, a big one, then you might want to do a performance-based,
Obviously,
alternative solution.
just like big picture, obviously, like our regulatory system is broken where we're not allowed to build sustainable traditional buildings. It happens with engineering and all the regulations. Is there any means, like, is there any avenue there, like permission from the planning minister or whatever, to be actually like having projects as research projects that allow it to be sort of exempt? And
you could try that. Eltham successfully in Victoria successfully lobbied that because there were 1,200 earth buildings, mud brick buildings in that area, that it was a significant cultural sort of site for earth building, and that they should be allowed to continue. And they had some sort of exemption built into it, I think, in Eltham.
There's also, Peter, there's still the pathway to pay for your modelling from an engineer. It's just that it costs tens of thousands of dollars.
Yeah.
So if you want to use another modelling package that's more sensitive to the sorts of things we're talking about for climate responsive design, you can do it, and it would probably get accepted. I mean, it would get accepted, but it's so expensive.
But also they have inside the new NCC 2022, they've really tightened up. You've got to model basically with any tool you want, but you've got to model it as if it's modeling how NatHERS models. So they're screwing it. Yeah.
So
they've changed that as well.
That's a new thing.
So just one question: if it's modelled up and it's deemed to satisfy alternative solution, would the creation of a new Australian standard that is based on this type of construction, is that something that is needed to change the culture?
Yes. I mean,
because the Australian standards is evolving all the time. And if one puts a bid to them, they'll basically put together a bunch of experts. That's what I understand.
I know. I've been on a panel of experts with Ray, and we've done it a few times, and with Steve Dobson as well. And it's a pretty painful process, and you don't necessarily get what you want out of it. You can't just write what you want and get a rubber standard. Yeah. So I think that's probably the last question.
Our next speaker is Verena Maeder. Verena is an earth building artisan with 32 years of experience in the construction of earth buildings. She is trained in architecture as well as building biology and ecology in Switzerland. She operates Solid Earth, an Adobe brick manufacturer in New Zealand, which has to date carried out 200 plus building projects. She also runs the Earth Building School in New Zealand that is dedicated to teaching the art and science of masterfully using natural local materials in buildings. Verena was the chairwoman of the Earth Building Association New Zealand from 2007 to 2014. And in 2017, she received the Tradeswoman of the Year award by the National Association of Women in Construction. She's currently part of the committee in charge of the revision of the New Zealand earth building standards and has contributed to the innovation of low density Adobe, which is now part of the code. She's now joining us from New Zealand. So welcome, Verena, over to you.
Thank you so much for that wonderful introduction. And thank you for having me back for the EBAA conference this year. In this session, I will talk about structural low density Adobe, which is earth building research and development we have been involved in since 2009. And I have actually already introduced and spoken about this at the 2017 conference. But today I will focus in particular on the thermal performance, since we're all keeping up with changing regulations and are dealing with legislators in different capacities. So thank you so much for having me. So I'm not going to say too much more about myself. The introduction covered that. I really want to speak to our mission statement, which is to facilitate the creation of healthy and beautiful buildings that don't cost the earth in the double sense of the meaning. So this is something that has been very close to my heart for many years, and I hope you can feel the passion that is flowing into my body of work. And I hope that with this presentation that, I will support some of you take the hurdles that at the moment we're facing in the industry. So just to give you a little session overview, we'll be connecting a little bit to our why again. It's useful. Why use earth and natural fibers in the first place? And then, of course, the main reason why I'm here is to talk about the Adobe Innovation, looking at low density structural Adobe for seismic areas in our case, and temperate climates, which affects many of us building with earth down under. We'll look at materials testing and thermal modeling that we have been involved in, and look a little bit at the Adobe manufacturing construction side of things, and then wrap it up with weatherproofing discussions. So to start off with, why use earth and natural fibers? And in our work, I'm referring to unstabilized materials in particular. And this is, I'm sure, is why we're all gathered here. And I don't have to convince anyone in this gathering, but I think it's still good to break it down and connect to our heartfelt why, especially when things are a little bit hard on the consenting front. Just referring to ongoing challenges and things that EBAA and EBANs, like the Earth Building Associations of New Zealand and Australia, are addressing. So very glad that we are convening both in person and online to discuss these things together. The sustainability factor, so like going into this why, the sustainability factor is what got me into earth building many years ago. And I'm sure that this is also the driver for many of you too, now more than ever. And the thermal performance is the main spotlight in today's gathering. Has been something that we have had to look at in depth. So the earth building materials often get lauded for their thermal performance in our circles. We have this mantra, warm in winter, cool in summer, and it still very much stands and is supported by anecdotal evidence, but it has to be looked at in a nuanced way. And this is all something we're examining further now. The healthy living aspect, the fact that, you know, Earth is 100% natural, it's non-toxic, VOC free, but above all, a really dry and dehumidifying building materials makes for very healthy living spaces. And this is thing that is probably most dearest to my heart because of my building biology and building ecology background. The health aspect of buildings in particular is something that as a company we really focus on, and also why we don't stabilize with cement. But this is a conversation for another day. And then the aspect, you know, of it being really suitable for self-builders, empowering people to build their own beautiful buildings, possibly saving costs along the way, the creation of local earth building businesses using local materials, and then really the dissemination of this really time-tested building material that is also easy to maintain and has long longevity is are all points that I think are important to remember when we talk about this. So the first three are things that I will talk about in a little bit more detail in this presentation. Going a little bit more into the sustainability aspect first. And again, you know, all of these things, of course, are things that we could go into much more depth, but the building material is 100% natural. It's often locally available, or, you know, in close vicinity even to the building site, in combination with waste stream fibers, like I am presenting with the low density Adobe material. We actually work with renewable resources that capture carbon even. As a whole building system, we're often looking at very low carbon footprints or carbon capture and an overall low environmental footprint. So like in terms of resource extraction, waste, transport distances, and so forth. And very beautiful, especially for the unstabilized material, is the fact that it is indefinitely reusable. So it is zero waste. It doesn't, at the end of the life cycle, it doesn't just go even just back to the earth or into a clean landfill. It can be reused indefinitely. We can make new earth building materials out of demolition material if we so chose to. Just to briefly touching on the health aspect as well. So I was saying, you know, like the earth buildings are really nice and dry. It's because earth as a material is hygroscopic. So it has an amazing ability to absorb moisture out of the air. So like a vapor, absorbing and dissolving moisture and really stabilizing indoor humidity. And this, as a, you know, knock-on effect, creates like a nice, dry, mold-free living environment, which, especially in temperate climates or in climates that are humid, maybe subtropical climates, is very important. So the indoor living spaces with earth, interior earth, get evened out at a healthy level of relative humidity. Then again, referring to the indoor spaces, off-gassing of materials, VOC and so forth, very low of any of these irritants. Like even natural materials can be high in VOC, so the volatile organic compounds, so that's things you smell. And some people react to even natural materials, but earth doesn't have any of this, so very low VOC, no off-gassing. And here we're already rolling over into like the thermal discussion, the thermal comfort that earth provides, both as a thermal mass material, but also because it is a dry building material, the human body actually feels more comfortable at lower temperatures in a dry environment. So the thermal comfort is influenced by this humidity regulating aspect as well. And now, you know, looking at the Adobe innovation in particular, So I am using the term structural low density Adobe and structural light Adobe interchangeably, just to make that clear. And the main point here I want to clarify is the structural. So this means load bearing. And sets this building method apart from other earth building techniques that are light. So like light earth method or straw clay or those kind of techniques that rely on a timber frame. So we're talking about load bearing Adobe block, but in lighter densities. And the structural light Adobe research and development project really started in New Zealand when the legislators increased the minimum required R values to R 1.0 for solid construction. And at the same time, they also increased it to R 1.8 for timber frame, light timber frame buildings. So that was back in 2009. At the time, they still differentiated between heavy construction and light construction. So there were two R values and both of them were raised quite considerably. And even though great performing earth buildings have been built for many years before that, also in our temperate climates using good design, it wasn't per se true that they were warm in winter and cool in summer, at least not in New Zealand. The thermal performance of earth buildings has always depended on various factors, many of which actually apply to all types of buildings. So I went, and like for this presentation, I had a quick look and looked at what are actually these things what are the factors that influence thermal performance. What comes up with a general Google search? What are our organizations talking about? And these are the things, like that we're talking about. Looking at it first from the point of view of the legislators, the Australian and also New Zealand approach have many similarities. So they talk about climate zones. So depending on where you are in our countries, there's different climate zones and different minimum insulation values. They also talk about the option of thermal modeling. And there is, in all these conversations, there's some pushback from the industry. So it's an ongoing political process where, increasingly we're looking at energy in use, and increasingly the legislator are upping insulation values, and they're going, maybe they're speaking a little bit about solar gain, like orientation of the buildings and so forth. They might talk about buffer zones. So that's when we go into thermal modeling, buffer zones in building. What they're not talking about, however, is thermal mass and embodied energy. And I think that really missing some very important points here. And I think our organizations, so the Earth Building Association of Australia and also the Earth Building Association of New Zealand, we have always presented quite a holistic approach to energy efficiency. So we've been talking about all these points many years, decades. We have maybe had a little bit of a blind spot when it came to the insulation values. So just wanting to name this. And we have been for years now been actively solving this because we can all agree that spending less energy on heating and cooling is a good idea, especially in this day and age. However, like the embodied energy is the big elephant in the room, and it is really what sets natural materials apart from other materials, especially natural materials that are locally sourced, so not transported very far, from other countries or whatnot across the continent. and especially if they're not stabilized. So if there's not high use of stabilizers such as cement. But all the other things we have been talking about, and we actually do well with our materials. So let's just look at this elephant in the room a little bit more, the embodied energy. And this is a graphic that has been produced by Bosch. It's a European research project on structural insulative cob. So in many ways, this project is comparable to the research and development that we have done with structural light adobe, just minus the funding and the stringent requirements we deal with here in New Zealand because of earthquake. And what we're seeing here is a life cycle assessment of different types of buildings constructed to various energy efficiency schemes or requirements. So you see, you know, there is the building regulations in green, there's passive house in light brown, Bosch down here, you know, they just, it's European. So they compared different energy efficiency programs with their structural light cob. And as part of this, you see they included embodied energy. So the steep incline at the start here is the embodied energy, and the rest is energy in use. So we're looking at the holistic, or like the combined energy use, both embodied and in use, of a building over maybe a 60-year time span. But this is happening now, you know, so because the main problem we are facing at the moment is global climate change. In most cases, a reduction of energy consumption will mean reduced CO2 emissions. So this has to happen as fast as possible. So omitting looking at embodied energy, to me, seems a real blind spot. You know, it is very important that we look at embodied energy, also of our earthen materials and the aggregates we use. And I will touch on this a bit later as it relates to our bricks. So just to orient you towards what we actually did, when we started the project of the research into structural light adobe, we were still working with the 1998 version of the New Zealand Earth Building Standards. It was 2009. So in the meantime, these have been revised. So on the image you see, it's 2020. There's a revised edition, but we were working with the 1998 version, which, by the way, is free for download. It's still up on Standards New Zealand. You just Google the NZS and the number, and it comes up free for download. And the nice thing, so we were working with materials and construction for earth buildings. There is a testing regime spelled out in the New Zealand Earth Building Standards, and following this testing regime, we developed all our structural materials. So it's very practical, and it was what guided us through the process of getting these materials developed and approved, and now even incorporated as a new earth building technique in the 2020 standard. So I have presented at the previous EBAA conference, and this presentation, I believe, is available on the channel. The presentation covers how we went about, you know, step by step developing the structural light adobe bricks. So I will only go into this a little bit now, and then really focus on what has happened since we last talked, focusing on the energy efficiency of the building and thermal modeling and embodied energy, which is data which we have gained since that last presentation. So just to explain to you what we did is we wanted to get the density, so the weight of the traditional mud brick. The weight is about 1,600 kilos per cubic meter. We wanted to get that weight down as much as possible while retaining structural capacity of the block. So we didn't want to go to light earth infill. We wanted to have a brick that was just as strong as a traditional mud brick, but much lighter, so that it had better insulation values. That was the brief. And then we tested many different light aggregates like straw, sawdust, wood shavings, pumice, vermiculite, paper pulp, and so forth. And the winning combo was wood shavings and paper pulp. So here you see, recycled paper comes in bales from local collection, and you pulp it with water. You achieve something similar with virgin paper pulp, but it's less, because it's a new product, it hasn't got as good environmental credentials. So we tried recycled paper pulp. And in the paper pulp, there's cellulose. So this is an extra binder that gives a lot of strength to the brick. And the fluffy stuff, the stuff that brought down the weight, was wood shavings. So sawdust didn't perform as well as wood shavings, similar product, but the shape of the light aggregate was important in terms of how strong the brick was. At the time, we didn't have, for example, hemshiv available. I think this could be tested and it could have potential. For us, it is still like way too expensive, so it's not something that we'll explore. But I just wanted to say, just because I'm talking about wood shavings, this is what we chose and what we have tested. Other things could be possible, and the pathway of finding out which mix works is following a testing regime. So the structural light Adobe bricks that we make are a combination of high clay content subsoil, so earth with high clay content, recycled paper pulp or virgin paper pulp, depending on availability, and then a big amount of wood shavings. And it depends how much, what density you're after would then depend, how much shavings you put in. So the exact ratios, I'll share our ratios with you, but the exact ratios will have to be determined depending on the R value you're after, and they have to be tested for your materials. You can't just reproduce a recipe in earth building. I'm sure you're aware of this. So our recipe could be a starting point, but it will depend on your particular scenario if you want to reproduce this. So for us, it is 1 part paper pulp, 2 parts clay, and 8 parts shaving. So lots and lots of shavings. And you see on the photo, it goes kind of fluffy, like crumble, and we mix with a backhoe. So that's how we make the mix. And then our setup here for the Adobe is a mold that makes, 20 or 30, depending on the size of the brick. And it's very much, we're mixing with the backhoe, we're transporting the mix to the mold, and then we're working by hand or with rakes. So it's definitely a manufacture. Works well for us. We find this effective, and then it's just air dried. So no extra energy going into the drying. So we made a heap of test bricks, and we took them through a series of tests. And the first, because the focus was on strength, we did the strength tests, and this is the famous figure 2.1 in 4298. So it's a figure that shows you, depending on earth building technique, what kind of tests you should be doing, and how many of them, and all the things, that the minimum requirements for parts. And here we just looked at Adobe, and we did flexural tensile strength tests for strength. The whole brick drop test is also for strength. It's sort of an initial thing you can do quite simply to see if a brick is has got potential, is good. Then we did wet dry appraisal tests and durability tests to see how they perform in wet dry cycling. And we had to do a shrinkage test and also like a bond range test for our mortar materials. And for us, the results came out really very, we were very pleased with the results. Just to make this clear, the B1 that didn't have such a good result, there was actually a brick we tested for a client. And then this SE 1 to 5, our solid earth 1 to 5, that these are our bricks. So we actually achieved, our average was a 0.99 MPa. The minimum requirement for this is a flexural tensile strength test, not a compression test. The minimum requirement is 0.4. So we achieved more than double, which is pleasing. And the reason why I've put the B1 in there, the only difference between these test results is how diligently the mixing happens. So the brick quality significantly increases with proper care being put into mixing and activation of clay cohesion. So not cutting corners, we mix 3 or 4 times before we mold the bricks, and that just really activates the strength of the clay, and it makes a difference when we test. So up to 2 times the difference. All the materials are the same in this. Because we were proposing a new building material, we also needed to do full-scale earthquake testing. This is not of that much interest to you, but just to say it did really well. We did this together with the School of Engineering of Auckland University. Gave us a lot of confidence in the material. So it was very good to see full-scale testing in plane and out of plane doing really well. Then we looked at the thermal performance, and the first thing that we had to do is get the thermal conductivity figures confirmed. Like, they exist in the international literature, but we needed to do the same thing to make sure that the New Zealand clay does the same thing as all the other clays. And that then that was done with Otago University. That then led to the development of this figure for the new standard, which allows us to determine R values depending on the density. So you see the 800, that's the kilograms per cubic meter of density for the bricks. That's what we aim for with our bricks. And then you read back and you get to the K value, which is the thermal conductivity of a 0.25. And then with the formula, this translates into insulation values for our bricks of 1.4 to 2, depending on the brick size and the wall width. So a more slender wall has less insulation value than a wider wall. And we wanted to aim higher than the minimum R value of 1 for solid construction at the time. And it is so lucky we did, because after all this, in 2022, they scrapped accounting for thermal mass in New Zealand. So no more differentiation between heavy and light construction, and they increased the minimum R value blanket for all buildings to a 2.0. So when they were in doing the public consultation on this change before 2022, they proposed 3 different models, options. Option one was, the minimum R value of 2, which we can achieve. And so we were like, we just scraped through with wider walls. We could still thermally model and do other things to pass, but, we just wanted something that was easy. But then they also proposed an option 2, which referred to a minimum R value of 3.6 in walls in locations such as Christchurch. So that's comparable to Hobart, And that would have been a little bit tricky without modeling. And that's why we commissioned the thermal modeling of a passive solar house compared to a reference house. And this was carried out by Dr. Marcella Browner. So she does modeling with WUFI Plus. And what she came up with was, if you look at the reference house, so we're looking at the walls, the 3.6. So she assumed the option 2, 3.6, and then she put in on the passive solar house with our bricks, the 2 for 450 wide walls. And she tweaked a little bit, with underfloor and roof insulation and glazing and so forth. But what she came up with was that the passive solar house design with 450 millimeter wide structural low density Adobe walls in Christchurch requires less energy for heating and cooling than the reference project that was specified to option 2. So really much bigger insulation value in the wall. She also did the same thing for Auckland, which is less critical. Auckland in option 2 still had a proposed R value of a 2.6, which I think, from what I understand, is what you guys are dealing with, something between these two cases. And for this, the passive solar house required substantially less energy for heating and cooling. And I would like to, for us, cooling is not so important. For some of your buildings, the cooling load will be important, and you see how this is different. It's definitely what I get out of this is that the thermal mass aspect is really important, and that thermal modeling confirms what we have always been talking about. So if you're interested, I can share this, the whole paper with all the graphs and stuff with you. You will definitely have to do a lot of thermal modeling, but I'm hoping that seeing these figures makes you hopeful. And just to wrap it up, going back to that embodied energy and carbon conversation from a little bit earlier on, it depends, what kind of materials go into these low density Adobe blocks. But for us, all the materials come within a 30-kilometer radius. They partially come out of waste streams. We use the tractor, but it's manual production and sun-dried. There is very little embodied energy, and the CO2, so the carbon, because of the content of wood shavings, they're actually carbon negative. They sequester up to 3 times as much carbon as the equivalent that would be used in the concrete foundations that are required for these heavier, solid walls. So this is, also something that gives me hope is, often go, oh, it's heavy, and then you need these big foundations. We can actually offset the foundations. And then from all of this, the conclusion was, it's suitable for load-bearing construction, even in seismic zones like we deal with, can be commercially scaled. It's actually easier to build with it because the weight is so much lighter. And they have good weatherproofing index, erodibility index, and they have a good thermal performance. They got included in the revised 2020 standard, which now covers more techniques, which is very pleasing. And the manufacture and the laying is as simple as ever. It's the same, totally the same, and that's what we wanted to retain, is the simplicity of this beautiful time-tested building technique. Beautiful Adobe, it looks nearly the same. It's just not as heavy. So maybe some of you recognize a couple of faces here. These blocks, if they were heavy Adobes, we would probably not be smiling, lifting them like this. But with the light Adobe, it's all good. So here, just to finish up, a bit of eye candy. That's the finished building there. And just as a last thing, really important to keep whatever goes onto the surface of the low density Adobe breathable. Because they're more fibers, we do recommend that they get finished in some way. So lime plaster, lime wash, or in sheltered or interior situations, an earthen plaster. So that brings us to the end of the presentation. Just really wanting to express thanks to everyone that has been involved in it. It's been an absolute pleasure working on this project. And yes, thank you so much for having me. Ngā nui, which means thank you very much, and kind regards and gratitude to you all, and also congratulations on your work and on your projects that you're coming up with. So nice to be here with you all. So I will just stop the sharing that so that I see you again. Yeah, okay, that's it.
Verena, have you got a minute for some questions?
I totally have time for questions. Sorry for going over a little bit. I talked fast.
Okay, so yes, John. Yes.
I'm just wondering, Verena, what sort of mortar mix you're using. Are you taking the same from the bricks to use in the mortar mix?
Yeah, we have used the same, and we have also reverted to just a traditional mortar mix. But both works. And for the mortar, the main thing for the mortar, we have to test. We have to do a shrinkage test, and we have to do a bond range test. So whatever mortar you use, compatible in materials, either just a clay, and we usually use a crusher dust, like a bigger particle aggregate, or the same material. The only thing with the low density mix is it dries a little bit slower. So it's not as sticky anymore. With the paper pulp, it gets kind of viscous, or like the mold release is really great, and it takes a little bit longer to dry. So that has to be taken into account when you use that for mortar.
So the bond wrench test is it's an earthquake sort of consideration, that the strength of the bond between the brick and the mortar.
Yeah.
That sort of have in our.
Yeah, like for us, we deal with a lot of shear or tensile strength, like deformation. But I honestly, like with wind loads and changing climate, I would still take care. So the most damage I've seen, apart from historic buildings that have had problems with earthquake, actually were wind damage to gable ends. So not to be underestimated.
Oh yeah, that's right. Is anyone else got a question besides John? So, yes.
You mentioned the significant finding of the mixing of the materials together to get the adequate strength, structural strength and shear strength. Was there some way of determining when it was mixed well enough?
So it's sort of an experience thing that we have, because over the last 20 years of producing bricks, we have to test every 5,000 bricks, and we just noticed, like, if we put in one more extra cycle of mixing, it becomes better. And when you break them open, so like the bricks, when they get destroyed, in the brick test, you look inside, and if there's still little sort of unactivated little clay balls in there, they usually are a little bit weaker, within reason, but rather it will depend on your clay too, because some clays just accept the water easier than others. But in general, we tend to mix all the materials together, let it sit overnight to hydrate, mix 2 times the next day, morning and evening, let it hydrate, and then mix 1 more time the next day. And that's just worked for us. You need to determine that for yourself with testing.
Can I just say that I think it's really important that what everyone does in all of these trials and, kind of guesstimations that we all do to achieve a product, it's really important I think, for everyone to be able to express what that those little magical, I don't know, kind of things are, because they are really valuable, and I think they would also lend us credibility, really, in being able to describe the work that's being done.
Yeah, yeah, I agree. And like, that's why I can't say this is how you do it. Like, there's many ways of doing it. There's a wealth of information and experience, and then there's testing, which gives you hard data to support something, and that's the beauty of it. Like, I like the New Zealand standard because it's open like that, and it actually was really supportive in this innovation, in this R&D, to just follow it and have confidence. And then we did the full scale testing, and that was a bit nerve-wracking because like, all of a sudden you see, what were those figures that we worked to actually useful, and they were, and in New Zealand we've had a couple of really big earthquakes, and they were like a real life test for earth buildings of the 1998 standard. And the engineers looked at many buildings, and not that much had to be tweaked. So the confidence in the testing really got solidified through these experiences.
Joe, did you have a question about load bearing and getting engineering done on load bearing?
Yeah, how to do that.
So Joe's had problem getting engineers to approve any sort of load-bearing cob.
Yeah, we need friendly engineers. Like, yeah. So the New Zealand Earth Building Standards, it's 3 volumes, and one of them is for engineers. And it's written for engineers. So any engineer that is open-minded enough to open it will understand the language and will be able to follow and calculate stuff following this standard. And I mean, for us, like the committee, the engineers that have been involved in writing these standards, they're getting older, and we definitely need, younger engineers to come on board with this. And just to, a little story about this, actually, when we did the full-scale testing, the engineering students they basically had to come with their professor, because the professor is friendly towards this, and he was all excited, and they were like, it will fail, and it didn't fail. Like, they didn't manage to just destroy the wall, and they got very excited about it. So show them show them earthquake testing, show them the standards, and talk their language, and hopefully we'll have some that come on board. But theoretically, actually, they should just be able to follow the standard and understand what you're going on about.
Or another question from John?
Yeah, Verena, I'm remarking on the fact that the wall failed along the mortar joints in the earthquake test, which is unremarkable in itself. I'm just wondering, what would it be partly due to the bonding, and that some sort of pre-prepping of the brick itself, like a dunking or a water spray? Do you do anything?
So, when you're designing to earthquake, we have steel reinforcing. We have to reinforce the walls. You can't rely on masonry. So, like, our cement bonded red masonry veneer has failed spectacularly in the earthquakes. It actually has given all masonry a little bit of a bad rap. The test is, does it fail and fall down on people or not? So you will have open, like the mortar joints will open, and you will have cracking. The bond will break. After big earthquake, you have to go back and repair that. So you're digging out and repointing. The main thing is it didn't fail. It didn't fall down. And the bond range test is not, it stands up to any earthquake. We're talking big earthquake, like the tests you saw there, where the wall deformed a lot. It deformed so much. It was 2 or 3 times the strength of the Christchurch earthquake in that test, because they loaded it. So they did a static loading with just G4, like just gravitational pull, and then they loaded more weight on the back of the test wall, and then they shook it. It was pretty spectacular, and like any masonry would open up, you know, like the bond would break, but it didn't fall down. And you know, in terms of workmanship of laying, yes, we dunk the bricks, you know, we do a good job. We also have horizontal mesh that gets embedded and so forth. So definitely you can do a good job of laying and have less of that happen in smaller events, you know. But it's repairable, and that's a beauty of unstabilized materials. They're very easy to repair and maintain.
I'm just wondering, just the whole experience of engaging with, you know, the New Zealand building standards and the authorities and the universities doing all the testing. Just wondering, you know, how arduous that entire process was in terms of time, expense, emotional energy.
Yeah, yeah. Look, I feel this. It was all sorts. It was a really mixed bag. So in terms of the engagement with the students and the apprentices, it was awesome. You know, after a bit of initial ice breaking, the revision of the earth building standards has been quite an arduous process in terms of not much funding, gazillions of hours of voluntary work on behalf of the committee, and a frustrating political process that now is coming to a good conclusion. And I mean, we were fortunate. It was just a revision, you know, like we already had the 1998 standard. We wanted to bring more techniques in, like sections on earthen floors and plasters, and it went from, you know, being this thick to being this thick. So it really got extended. We made the most out of the opportunity of having to go through this. The problem was, you know, it was a political problem that the legislator came back to us after Standards New Zealand had ticked it off and printed it with more questions. So we had to reopen the revision process, and it's nearly done. So like, yeah, that was frustrating. But I think ultimately it actually has led to an even better standard now, because they nitpicked it and they listened. Like in the end, I think they listened. I don't know how much difference it will make to the building industry as a whole, but like, you know, we fought and it was worth it. Yeah, but it took years, you know. So I think, you know, having gatherings like you have now, and like really supporting each other, and you're in this for the long haul in a way. And then, you know, like there is actually value in saying, you know, there is the New Zealand Earth Building Standard, and like referring to more international stuff, especially if you can actually compare, you know, like the situations. And I think the situation with the climate, for example, is comparable, you know, like New Zealand just is more extreme in terms of wind-driven rain in most places and earthquake. So if we can do it, I think you guys can do it too.
Yeah, you make us look easy, I reckon.
You know, I mean, like maybe your legislators are a little bit more annoying than ours, but ours were, I shouldn't say this officially.
I think we're just about done with questions, and I'd like to thank Verena again. It's been
welcome. Thanks for having me.
okay.
Have fun.
Thanks, Verena.
Thank you so much.
Thanks very much.
Really nice seeing you all. Bye. So I'll leave now, okay? Bye.
All right, just a quick introduction on Ryan Strating. Now, Ryan is an architect and founding director of Co Collective, his practice in Tasmania. His award-winning practice focuses on making architecture that has low environmental impact and healthy environments for its occupants. Ryan is also the founder and technical developer of Clinker, which is what Ryan will be talking about today. Now, Clinker is a natural, lightweight, expanded clay aggregate. It's been used as insulation for different building assemblies. And Ryan has successfully used Clinker in rammed earth walls to improve residential thermal performance to achieve more than 7 stars. And Ryan's business now imports and sells Clinker from Europe, I believe, to Australia. So over to you, Ryan.
Thank you, Susan. Yeah, great presentations. Thanks for inviting me to the conference. I would have liked to have been there, but yeah, presenting today from Nipaluna, Hobart. We've got a few projects underway and it was tricky to get away. Before I start the presentation, I always like to pay the respects to the Palawa people of the Tasmanian Aboriginal community, whose land on which I am presenting this talk. The talk that I'll be presenting today has a relatively limited scope and it relates to the work that we've been doing with expanded clay aggregates as an additive to rammed earth to reduce the density and improve thermal performance. It's a work in progress and yeah, we're making contact with various people in the building industry and we're keen to get feedback from those and also conference attendees about how we might improve this technique and what options we might have going forward. And at the end, I'll talk about some future options and perhaps we can talk about those in the question and answers at the end. So I'm a bit of a generalist, not a specialist, and very, very open to conversations and input. I think it's good to start with a bit of background about the work that I do as an architect and with Clinker. Our team at Core Collective has been designing and building energy efficient and healthy homes, mostly in temperate and cool temperate climate zones and mostly in Victoria and Tasmania for about 25 years. We mostly work in climate zones 6 and 7, and we build houses that use very little or no energy to keep them within a comfortable temperature range, typically achieving between 7.5, 9.5 star ratings for our houses. And I agree with Marci and others about the limitations of rating systems, but after 25 years, we get a pretty good sense of whether the rules of thumb are working and how we can implement those in future. So a lot of the rules of thumb that we use in the practice, they work in practice in occupancy, but they also work to achieve relatively good energy ratings. And we use a combination of traditional passive solar design principles and quite well insulated building envelopes, and usually high levels of internalised thermal mass along with natural ventilation. We're pretty lucky, climate zone 6 and 7. If you don't live in it, you might think it's cooler, but it's a relatively benign climate relative to, you know, cold European climates and climate zones 8, where so we're building to a relatively high standard, but in a relatively mild zone. So in search for various beautiful low impact materials that are robust and fit for purpose, we've used traditional construction methods as well as low density masonry such as Hebel in the past, not so much anymore, and also modified lightweight concrete and insulated and uninsulated rammed earth. We typically use timber frame windows that are double glazed or triple glazed, and we insulate both under the slab and at the slab edge. It's pretty rare we don't do that in those climate zones, and we find it has quite a good outcome. We use light coloured roofs or green roofs or gravel ballast roofs to ameliorate summer heat and also keep the winter temperature in. Another part of our practice is working with heritage buildings, and you can see it might be of interest to the attendees, the building in the top right. This is the oldest Pisa building in Australia, and it belongs to a client of ours, and it's in the central, northern Central Highlands or Midlands of Tasmania. And we are currently working on some options for renovating that building, but it's interesting to visit and see what's effectively a round earth building that has been continuously occupied for nearly 200 years. It was built in 1826, I think. Fascinating building. So the most, it's the two images you see on the top left and top centre. That's my own home in Hobart, and it has an energy rating of 9.2 stars, and it was built with rendered blocks that are made out of lightweight concrete, so clinker aggregates in concrete masonry units that have got a density of 600 kilograms per cubic metre. It's fully buried at the south end, and it's insulated underneath the ground floor slab and behind the buried portions with about R2 of clinker expanded clay. It's got excellent cross-flow ventilation on the upper floor, and we've got an internal recirculating system that moves the air around from upper to lower floor depending on the season. It's triple glazed. It's often passively warm at around 19 to 21 degrees in winter, even when it's below freezing outside and snowing, and it often will maintain that temperature for 2 or 3 days, even without any input of sunshine in winter. So it holds the warmth very well and keeps it out very well in summer and the shoulder seasons. Excuse me. So the most reliable way we've found to optimise year-round thermal performance of the buildings we build in these climate zones is to add mass internally and to add insulation to the building perimeter, so improving the performance of walls, windows and roof. Our personal experience has been based on living in many of our own designed houses, and we've noted that if you add insulation to the external perimeter at the design stage while not diminishing the internalised thermal mass, then you can build really comfortable buildings without reducing the environmental performance or compromising on beauty. This is expanded clay. We call it clinker. There are some samples that I sent through that's of the crushed version, which is going to be the part of that we talk about with the round earth. I'm part of this company called Clinker for the last 12 years with a couple of expat Europeans and another Australian person, and we work with expanded clay products. They're made using a very particular type of clay that's popped in a continuous kiln process where the clay particles are broken up into small managed moisture content and then heated to about 1200 degrees Celsius, and the particles begin to fuse and melt. And at the same time, the gases that are generated inside the particles expand rapidly to form a honeycomb of small cells. So the resultant material's got a really low particle density, but it's hard and strong. And it has an internal pore volume that's sealed and a hard ceramic external shell. And the particles, when they come out of the kiln, they vary in size from dust up to about 20 millimetres in diameter, and they're graded in the factory for various uses. The bulk material in the size range of 10 to 20 mil, for instance, has a particle density of approximately 230 kilograms per cubic metre, so it's quite light and still very strong. Here you can see the crushed material on the left that there is a sample of there, hopefully with you, and on the right, the relatively round particles, sometimes round. And they've got multiple uses, underslab insulation, retaining wall backfill, as I said, and also reducing loads on retaining walls, so backfilling with lightweight material that's free draining rather than heavyweight gravel. And it's also used for civil applications like bridge abutments and stabilising swampy sites for roads and other structures. However, today I'll be talking about the product on the left, which is the crushed aggregate and how it can be used in rammed earth construction. These are some of the walls of the building that we've built, or this was when it was under construction. So the idea with this house, it's in Cygnet in southern Tasmania, and it was completed in 2022. The idea was to use expanded clay aggregates as a proportion of a normal stabilised earth mix, which is what our local contractor uses. So we substituted heavyweight aggregates for some lightweight aggregates. And using some NatHERS or accurate modelling that achieved 7.3 stars. And it's performing well in use as well. We have contact with the owner, and there's very little input of electrical energy to maintain a comfortable indoor air temperature. And the clinker products are 100% natural, so it adds to breathability in the walls and contributes to a healthier chemical and mold-free indoor environment. And in addition to increasing the R value of the rammed earth by trapping the air, the performance of this building and any building should be seen holistically, not just in terms of the performance of the wall components. So in this building, I think here's an example, different building, but it's an example nonetheless of using under slab and slab edge insulation, using clinker lightweight masonry and bulk clinker expanded clay fill under the floor. And in the Signet House, adopting passive design principles such as good amounts of north glazing, reducing glazing area to the other facades where possible, using airlocks at the main entry to buffer leakage when coming and going, and making sure that glazing has excellent performance to suit the climate. And with this project, we also had a green roof that is lightweight and free draining, and it also uses crushed clinker as the growing media, or 75% of the growing media, with biochar sands and some organic material. As a bit of background, it's interesting to look back at the long history of stabilised walls that have used lightweight aggregates. So there's a couple of examples that I'm going to show you. Typically they were used to improve structural performance, not thermal performance, but they're interesting nonetheless in that what we call Roman concrete was actually a placed material which was packed between permanent forms, and it was made from slaked lime, volcanic ash and aggregates, and the aggregate was often naturally occurring pumice stones, which is lightweight volcanic rock, which has usually a higher density than clinker aggregates, but much lighter than standard gravels. And this mixture was placed between permanent forms of stacked stones or masonry. And in some cases, timber formwork was used, and the lime-rich matrix is strong and light and somewhat self-healing in terms of cracking, and has excellent long-term strength and durability, especially in saltwater environments. There's still examples in the Mediterranean of in ocean structures made in this manner. So at the Baths of Caracalla in Rome, which this is a photograph of the ruin, it was completed in 216 AD, and it uses lightweight aggregates in the composition of the placed and compacted wall system. And they increased the density, or decreased the density of the aggregates towards the top of the dome, and this allowed for thinner structures and longer spans. Also in Rome, Pantheon, which was built in 126 AD, it also employs low-density structural Roman concrete in the walls and the dome, and it also gets progressively lighter towards the top and achieves a span of over 40 metres. It's still intact 2,000 years. So how this is instructive is in terms of, I think, life cycle carbon value per square metre. I think given the lime-rich walls also absorb CO2 over time, it's a really important lesson in material specification, building physics, and designing a building that is going to have a long serviceable life. Closer to where you are, the Australia Square in Sydney used lightweight aggregates in the concrete to achieve thinner and longer spans and less deflection. The building was designed by Harry Seidler, but the structure by Pier Luigi Nervi, it's stunningly beautiful, and the geometric forms that are inspired by nature have a practical reason for being, and the concrete has reduced loads from the lightweight concrete elements. But today we're using clinker expanded clay lightweight aggregates in place of pumice because it's got controlled performance characteristics and consistently lower weight. clinker aggregates are less than 3 times lighter than the weight of naturally occurring rock aggregates. And they've got well-defined structural and chemical properties, so it makes the reduced density walls that are high performance and also lightweight without losing the solid feel that you get from a standard density rammed earth wall. This is the photograph of the recently completed Signet house, where we created the lower density material with expanded clay aggregates and also using crushed recycled concrete, which we can get in a controlled form locally, which is really great. This blend was specified by the local contractor. They don't use clay in their rammed earth walls, but use sometimes some soils, but crushed recycled concrete and sand, and then this clinker replaces some of the aggregate material. In this case, it was 45%. Prior to constructing the house, we did some samples with the Unique Earth Tasmania, who was the contractor. Initially, they did 2 small panels, one with the round clinker aggregates you can see on the left-hand side, and the crushed sharp clinker aggregates in the sample on the right. We found that the round material comes loose in the facade, in the face of the material, in the finished wall. It looks pretty cool, but the crushed version was much more durable. So we prepared a larger sample. Unique Earth did this with their preferred mix ratio, and we stuck with the 45% clinker blend, and so site blending, damped, or get the right moisture content, and then just their normal methodology, which is formwork and pneumatic rammers. The sample wall was successful. We had a robust matrix. It didn't decompose on the surface. We got 8 MPa cylinder testing. The client liked the colour. They'd specifically requested that they didn't want to have an orangey or a red coloured wall, so they were very happy with this kind of pale, warm tone. So then we proceeded to construction, and we adopted the same composition and placed it in lifted forms in the normal manner. Some of these chamfered walls, openings and reveals were fabricated, of course. And it was built, we did some calculations and worked with ABSA and found that 500mm thickness was going to give us the thermal performance that we needed. So we didn't need any insulating polystyrene core, which 20 years ago we did some polystyrene insulated rammed earth, which is obviously not ideal, but this was at least on paper and also in use performing quite well without that XPS core. For the internal walls, we used 150mm clinker blocks, which are a low-bearing, lightweight masonry, about 2 MPa and 600 kilos per cube. And it's quite sound resistant, and the end wall was lime rendered and lime painted. The blocks have got a 4-hour fire rating, so they're great for dividing between tenancies or, in high bushfire rated areas. They're very durable in the fire system, bushfire prone areas. And these blocks have also been used by our clients as a plinth for hempcrete houses, where they don't want the hempcrete to sit too close to the ground because of durability issues. And we use this as an insulating plinth layer to get up to the appropriate height. When we're delivering this product, it currently comes from Europe. We are looking at a longer term plan to establish manufacturing here in Australia, but we have to unfortunately wait for the maturity of the hydrogen industry, but luckily that's underway because we would want to establish the factory with the kilns powered by or fueled by renewable green hydrogen. So it will come down quite a lot cheaper when we're manufacturing locally, but currently it's $1,600 for one of these big bags. We deliver them for that price in most places, nearby capital cities. It's about $640 a cube. works out to about $160 a metre square of wall, and we just deal with larger quantities. But if you're buying the minimum order, you can build around about 220 square metres of wall, 500 thick, at 50% of the wall matrix. So we haven't done a direct comparison, but with the local contractor compares it favourably with XPS panel because they don't like working with the XPS, and it can be frustrating ramming either side of it, and obviously they prefer to work with natural products where they can. The house rated 7.3 stars. It was a couple of years ago, so before these NatHERS libraries have been updated, which Peter was talking about earlier. I'm looking forward to testing some of our existing buildings using the new library materials, but we built all the energy rater used in consultation with ABSA. They constructed a kind of proxy wall based on other materials that they have in the libraries to simulate the performance and density of the clinker optimised rammed earth. And I think partly the good passive solar design, partly the good quality windows, the highly insulated green roof, but in concert with that and the rammed earth external walls, we think it's a pretty good result. So in terms of how we move forward with this testing, this is the first test of this type that we've done. We're curious about doing more. We obviously would like to get away from cement stabilised rammed earth if possible. It'd be really interesting to talk to some of your members about doing some small scale testing where we could provide a small amount of material and see how it might work with a clay binder or perhaps geopolymers like fly ash. I'd be interested to hear everyone's thoughts on that. So we can also, so the first point there really is around improving thermal performance by adding even more of the clinker into the mix. We feel like it would be interesting to test up to sort of 60 or 75% of clinker in the matrix and just see how it performs, how it holds together, what the strength is, and those tests are yet to be done but are coming up. And yeah, the local production that we mentioned in Australia, which is a future development. So I've kind of zoomed through it pretty quick, but really interested in taking some questions from the audience or discussing, hearing people's feedback about this methodology.
Okay, so
Yeah.
Ryan, can I get you to stop doing your screen share, please?
You want to see?
Good. All right. Okay. All right. I'm sure we've got some questions from the rammed earth guys.
So you said you achieved about 8 MPa in your rammed earth clinker mix. I was wondering, do you know what the contractor achieves normally without the clinker in that same, in an equivalent mix? Do you know what MPa he would be?
I think it was more or less the same.
Yeah, cool.
But we're building heavy lightweight masonry walls with solid clinker concrete. So where the clinker, you saw those 150 clinker blocks in the photographs, we're using a 250 version of that. And they have 2 MPa and we're using that up to 2 stories. So I feel like, and interested to hear everyone's thoughts, but we could go well under 8 which would happen when we improve or increase the proportion of clinker in the mix, but it would get better thermal performance.
Are there any other questions? Not you.
I was going to see if, so with your walls, did you do a thermal performance on that to get the NatHERS rating? Like how was that 7.1 stars established?
They developed because of the low density concrete in the libraries, in the NatHERS libraries when we did this reporting, there's a method whereby you can create a proxy wall that builds up a composite that mimics the density and the performance of the wall you're trying to mimic. So the process there is the energy rate that to ABSA, and they get approval for the proxy. And that's what we did up until this point now, when if we have, I'm not sure, I haven't even looked at the new NatHERS libraries, but I'd be interested to know what densities are listed, whether they are incremental by sort of 50 or 100 kilograms per cubic meter increments, or whether there's a sort of more broad range, but it should be relatively straightforward.
Notice that Verena in the New Zealand code, they've got a graph, so they can go in there and pick whatever density they got and read off it. But they don't have NatHERS, so it's a bit. I don't know how that'd work in Australia, but it'd be interesting. I hope we haven't made it harder for you with the inclusion of the values. I hope they're sort of what the ABSA people came up with, but the fact that the values are in the library means that it's easier. You don't have to go through a more costly process, and it's advertised out there. It's more, people see it and say, "Oh, what's this?" and assessors will see it, and yeah.
Are the clinker blocks made in Australia, or are they imported as well?
They're currently imported. We find we did some cost benefit analyses on bringing in bulk clinker and then making the blocks, but because the Danish and Norwegian parent company are so good at it and they produce such large volumes, it's impossible to get near it on cost. And they do arrive, we tend to deliver directly to site. So they arrive on palletized, and that process is pretty hard to beat until we start manufacturing everything locally.
And is that just clinker and cement? What's the...
Yeah, it's like a no fines concrete. So if you pour water on top of it, it'll run straight out through the bottom. But the benefit being, once it's rendered, we use breathable renders. If there is moisture in the wall, it doesn't wick up through the block, and it also adds to that internal and external pour volume that gives it really good thermal performance. So it's a small amount of cement, water, and clinker aggregates in a 2 to 10 millimeter range. Really easy to lay. They're a pleasure to work with, really.
Any more questions? John?
Could you comment on the maximum clinker, I guess, crush that you'd include in cement, just to give some sort of idea, and then comment on what you see in the difference between cement and crush, render. What the specifications are different. How you would, what people are ordering for the two different applications, one for cement and the other one for render.
Oh, concrete. Well, it depends on the application, and as Verena was saying, it really comes down to the company or the builder or the contractor who's using the product themselves. We're not selling them necessarily a finished product. If we're selling them bulk aggregates, we can give them technical advice, but it really comes down to testing. So if one example, for instance, we're using crushed. There's a concrete company in Queensland that's currently testing to make septic tanks out of crushed clinker concrete. Now, interestingly, they're doing it because they want to be able to put 4 tanks on a truck instead of 3. They've got a maximum weight for their trucks. So their usage is not about thermal performance or strength, it's about transport logistics. And so for them, we give them some technical advice, we give them some product to play with, and when they get their mix ratios right, they just order the bulk product. That's one application. The other is, no fines concrete for backfilling retaining walls. You might put a little stabilized cement in that. But yeah, it really varies. It varies on what people's uses are for the product.
Yeah, Ryan, I was getting better reductions in weight by using larger sort of aggregates or larger lumps of like larger hemp hurd. did they try to use larger clinker and take out the large aggregate, the recycled concrete aggregate, and put more recycled sand or sand in and use the clinker as the aggregate, and see if that could stop the balls going to the outside surface and change the mix up from what they're used to blend one specifically for clinker. Is that how you look at introducing more clinker into the mix, or?
There's probably two ways to approach it. I'm not confident that the round balls won't migrate to the surface and pop out anyway, but I think it's worth testing. They also aren't, the bigger the particles, the less strong they are, and depending on how you're ramming, you might smash them anyway. Big pneumatic rammer. Or it might just push it into the moist soil or moist matrix below it. I don't know. I think there's so much more testing to do. If we look at the Roman concrete example, what's really interesting about that is it's all placed. So there were very large particles of pumice in the Roman concrete in a complex matrix of binder. So there is, depending on the contractor's appetite for work, but I presume they're all pretty hard workers, you could be placing larger particles in the central portion and sprinkling them in a layer as you ram in the kind of smaller particles, which could still include the crushed clinker. So there could be a more like a hybrid system, which I think would perform better. But you could keep particles away from the face by placing them in the lift.
In terms of the current production, you said you're waiting for hydrogen come on board. Is that to do it in Australia, or are they using hydrogen currently, or how are you running the kilns, and what sort of energy?
Yeah, sorry to interrupt. The kilns that are already running that produce our material are running using traditional fuels. So, gases and liquid fuels. I think the transfer across to hydrogen in Europe is not happened yet. There are some biofuel powered kilns that are using waste industrial materials or waste organic materials to power them. But the next generation of kilns, and we're talking to the producers, are more likely to be adopted in new installations. These industrial processes aren't normally upgraded if something's already using, which is hence the slow change with carbon emissions. There's a lot of inertia in the system. We would love to get started tomorrow with production, and we do have a hydrogen partner, but we're waiting for him partly, and we're also waiting, it's a very big investment to get the plant up and running, and we need to make sure also that we have a market for the product, because it's only really efficient to make it if you're making it 24/7, and you end up with hundreds of thousands of cubic meters per annum. So I need you guys to use a lot of it, and then we can
Do you know what the current embodied energy is in producing it at the moment?
We did some I'm not an expert in any of that, but we did do some work with eTool in WA, and we also did some work where we analysed we analysed it specifically in relation to XPS. So in terms of the provision of insulation in a wall, it's not dissimilar to the embodied energy of XPS to achieve the same insulation, but obviously it's a natural product. And the benefit that I see as a kind of designer and builder, and a person who is seeing, as I get older, seeing buildings that are pulled apart, a clinker rammed earth wall is a useful thing. Once it's smashed up, you can reuse it, and it's not dangerous or harmful. It's really easy to recycle, and it, in fact, it's going to have a higher end use or value than standard gravel.
Could I ask a question? On the picture of the Signet house, it looked like the inside ceiling on the inside picture was the same colour and texture as the walls. Was it?
The ceiling?
Yeah, the inside ceiling looked like the same colour and texture as the walls in the Signet house. In other words, the rammed earth walls and the underside of the ceiling looked the same.
It's a painted ceiling, so it's
Okay,
painted
thanks.
so it's just a colour choice.
So it was a concrete roof, was it?
No, it's a timber framed roof with a trafficable membrane and then drainage layers and a green roof on top, but then it's lined underneath with plasterboard that's painted with a lime paint.
Okay, thanks.
LVL roof structure.
Any other questions?
Not so much a question, but I think we'll be in touch.
I've got some, Ryan sent some information brochures down too. I've sent the sample of the wall and the sample of the material around the room. So if anyone wants, how many of these are there, Ryan?
The flyers or what have you got there?
A little bag of leaflets to do.
That's all there is. But I more out, just if anyone wants some information, just get.
Maybe people who are really keen to have them.
Could I just ask? Could I ask one more question? Ask another question.
Sorry?
Can I ask one more? You measured the star ratings and NatHERS. Did we miss it, or the ones the testing that Verena was talking about? You were talking about with conductivity and the R values. Have you got that data as well, or is that from
data's on that?
That's the data, is it?
Data's on there. Yeah.
It's estimated based on the component materials in the wall, and the way that the rammed earth rater did it was they used the wall proxy, which was a combination of standard rammed earth and a bit of Hebel to as a composite wall that mimicked the performance in the software, but because we didn't have standard.
Yeah. So you didn't physically do those tests like that?
No.
None of that. Yeah. So that would be good to do, would it not?
Oh yeah.
Yeah.
What density you're working with? About 1,600 or a bit lower?
So the product, just to clarify, the piece of broken material you've got there, I think that was a 40% blend. You can't actually see a lot of the clinker in the sample, but the product that we made was 45 to 50%, and we're looking at doing them with greater proportion of clinker in the blend. Yeah, the performance of the wall that we built was 1,550 per cubic meter.
We've got 1,600 in there, 1,000 and 650. So the 1,600 is pretty close.
It'd be nice to get a 1,250 in there because I think, or even say 1,350, because I think that's a really good goal for something that's achievable and still strong and doesn't break down on the surface. So I don't know whether there's an opportunity for them to do other sort of intermediate values in the library, but that'd be handy.
Yeah, there are other. They said that we can put more densities in there if we wanted to.
Great.
I think once we've got the door open, once we get the foot in the door, we'll probably do it more easily than starting, from scratch. So, are there any other questions before? Yep, one more.
I might have missed this at the beginning, but just wondering, like, how long the company's been around, how many houses like using this abroad or in Australia?
So our company's been around for 12 years, Clinker. My architecture practice has been around for 25 years. In terms of the expanded clay products, the product itself was invented in Denmark in the 1940s, and they use it quite a lot in lightweight concrete in Europe. In fact, I was thinking there might be some benefit in looking at what the European norms say about low density concretes, because there's quite a lot of work done and it could be easily transferred across to earth building because it really just relates to density. So if you said, okay, look, you're looking at what they're doing in Germany and Austria and Switzerland with low density concretes using these aggregates, and then transfer look at how that they model their performance, because they're building buildings that are solid external walls of lightweight concrete that looks like concrete, which, effectively is a similar thing in terms of how the performs. And they're doing it under a much more stringent regulatory environment. So I reckon there's some low-hanging fruit there for kind of leveraging the local bureaucrats into, and I think I've heard that this is a possibility for the future, is that we could, in some situations, building certifiers and building surveyors can adopt the European norms in place of Australian standards for certain elements under the National Construction Code or as a performance solution. So I think that there's some probably quite easy and fruitful research to be done on that.
Is there any other questions? No? Okay. Ryan, thank you very much. We've passed around the samples. We've given out the brochures, and I think you might get some phone calls shortly from some Round Earth guys by the sound of it. So thank you very much for your presentation. And